In 1991, a network of underwater microphones operated by the United States government picked up a sound rising from the Pacific Ocean. It was not a whale. It was not a ship. It was not an earthquake, not a storm, not any instrument of human industry. The sound climbed in frequency, like a slow, deliberate breath drawn upward through water, and it repeated over and over again, cycling through its strange ascending pattern with a regularity that suggested something purposeful. Scientists at the National Oceanic and Atmospheric Administration catalogued it, analyzed its waveform, and gave it a name. They called it Upsweep, and then they waited for it to stop. It did not stop. Upsweep continued through 1992, through 1993, through the rest of that decade and into the next. It persisted through the turn of the millennium, through the early 2000s, through the years when wars were fought and governments changed and entire technologies were born and discarded. It was still there in 2010. It was detected again in 2015. Decades passed, and the sound simply kept going, a patient rhythmic signal echoing through the deep Pacific with no confirmed origin and no satisfactory explanation. No one built a machine to produce it. No one turned it on. And despite more than 30 years of recording, no one has conclusively determined what is making it. The sound preceded many of the scientists who now study it. It was already ancient in terms of continuous monitoring by the time some of them entered graduate school, and it remains to this day a fixture of the deep Pacific acoustic environment, as constant as the currents and as unexplained as the day it was first identified. Consider the weight of that statement. Humanity has developed instruments capable of detecting the faintest acoustic whispers across thousands of kilometers of open ocean. The hydrophone arrays deployed during the Cold War were sensitive enough to track individual submarines moving beneath the surface of entire ocean basins. These systems can distinguish between the low rumble of a distant earthquake and the song of a blue whale calling from the other side of the Pacific. They are among the most refined listening devices ever constructed. The engineers who designed them pushed the boundaries of what was physically possible in terms of sensitivity and range, producing microphones capable of hearing the ocean's quietest whispers. And yet, when those instruments captured a sound that has been repeating for more than 3 decades, the best scientific minds in the field could not definitively say what it was. They could describe it in exquisite detail. They could measure its frequency, its amplitude, its duration, its seasonal patterns. They could tell you when it was loudest and when it faded, but they could not tell you, with certainty, what was making it. The ocean, which covers more than 70% of the surface of this planet, remains a place of almost incomprehensible mystery. More humans have walked on the surface of the moon than have descended to the deepest points of the sea. The darkness below 200 meters is so total, so absolute, that no sunlight has ever reached there in any meaningful sense. The pressures at the average depth of the ocean floor would crush a human body in an instant, compressing bone and tissue with a force that makes survival impossible without the protection of specialized engineering. And within this vast, dark, pressurized wilderness, sounds travel with extraordinary efficiency, moving at nearly 1,500 meters per second, roughly 4.5 times faster than they move through air. A sound generated in one part of the deep ocean can, under the right conditions, be detected on the other side of the world. The ocean is not silent. It is full of noise, full of signals, full of voices both identified and anonymous. But some of those voices have no known speaker. Upsweep is one of them, and it is the most persistent of them all. By the end of tonight, you are going to understand what this sound is, where it was detected, why it has puzzled scientists for more than 30 years, and what its continued presence tells us about the limitations of human knowledge. You are going to learn about the Cold War technology that made its detection possible, the volcanic landscape that may hold the answer to its origin, and the strange acoustic properties of the deep ocean that allow a single sound to travel across an entire basin of water without fading into silence. You are going to encounter the other unidentified sounds that have emerged from the deep, each with its own mystery and its own unanswered questions. And you are going to confront a simple, unsettling truth that the planet beneath our feet and beneath our oceans is still producing phenomena we cannot fully explain, phenomena that have persisted for decades in plain acoustic sight, recorded and catalogued and studied, yet still not understood. Before we get started, if you find these mysteries as fascinating as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. What follows is the full story of the Upsweep sound, from its first detection to the present day, from the Cold War listening stations that captured it to the volcanic ridges that may be generating it. It is a story about sound and silence, about what the ocean reveals and what it withholds, about the strange and beautiful arrogance of believing we understand a world we have barely begun to explore. It is a story about a planet that is still speaking, in frequencies most humans will never hear, from depths most humans will never reach, with a patience that makes human curiosity seem fleeting by comparison. The deep Pacific has been patient with its secret. It has held this sound through decades of recording. It has offered clues, each one tantalizing but incomplete, each one pointing toward an answer that dissolves when examined too closely. Tonight, we follow those clues as far as they lead, into the darkest waters on Earth, to the edge of what science knows and the beginning of what it does not. Now, let's begin. To understand the Upsweep sound, it is first necessary to understand the medium through which it travels, the ocean itself, a body of water so large, so deep, and so poorly understood that most comparisons fail to capture its true scale. The ocean is the dominant feature of this planet. It is the thing that defines Earth when seen from space. The blue that overwhelms the brown and green of land, the shimmering expanse that distinguishes this world from every other known body in the solar system. And yet, for all its prominence, it remains the least explored major environment on the planet's surface. The ocean covers approximately 361 million square kilometers of the Earth's surface. That figure, written in full, represents an area so vast that it dwarfs every continent combined. All of the dry land on Earth, every mountain range, every desert, every forest and city and plain, could be placed within the boundaries of the Pacific Ocean alone, and there would still be room left over. The Pacific, the largest of the 5 ocean basins, spans approximately 165 million square kilometers, an area larger than all the world's land surfaces put together. It stretches from the Arctic to the Antarctic, from the coastlines of Asia and Australia to the shores of the Americas. And within its waters lies the deepest point on the planet, the Challenger Deep in the Mariana Trench. The average depth of the global ocean is roughly 3,800 meters, which means that if you were to somehow drain all the water and stand on the exposed seabed, you would be looking up at a wall of emptiness nearly 4 kilometers high. That is more than twice the height of the tallest building ever constructed. It is roughly the altitude at which commercial aircraft begin their descent. It is a distance so great that a person standing at the bottom would be invisible to someone standing at the surface, even on the clearest day, not because of the darkness of the water, but because the curvature of the ocean floor and the sheer distance involved make visual contact impossible. Mount Everest, the tallest point on the surface of the Earth, rises approximately 8,849 meters above sea level. It is the peak that climbers spend years training to summit, the mountain that claims lives every season, the geological feature that symbolizes the extreme limit of terrestrial altitude. If you were to take that mountain and drop it into the Mariana Trench, the deepest known point in the ocean, the peak would still be submerged beneath more than 2,000 meters of water. The mountain that no climber can summit without supplemental oxygen would vanish entirely, swallowed by depth that makes even the tallest terrestrial feature seem modest. That remaining 2 kilometers of water above Everest's hypothetical sunken peak would itself be deeper than many of the ocean's abyssal plains. The scale defies intuition. To grasp another dimension of this scale, consider time. If you dropped a small metal weight from a research vessel at the surface, that weight would take roughly 1 hour to reach the bottom of the Mariana Trench, sinking through more than 10,900 meters of water. During that hour, the weight would pass through every temperature zone, every pressure threshold, and every boundary of light and darkness that the ocean contains. It would begin in warm, sunlit water and end in near-freezing blackness at a pressure exceeding 1,000 atmospheres. 1 hour of uninterrupted sinking, and still the bottom would seem to arrive slowly, reluctantly, as if the ocean were unwilling to reveal its floor. The ocean is not a single uniform space. It is layered, stratified, divided into zones that differ so dramatically in temperature, pressure, light and life that they might as well be separate worlds stacked one on top of another. Understanding these zones is essential to understanding how sound behaves in the deep ocean, and therefore essential to understanding why a sound like Upsweep can travel so far and remain so difficult to trace. The uppermost zone, the epipelagic, extends from the surface down to approximately 200 meters. This is the sunlit zone, the layer where photosynthesis is possible, where warmth from the sun penetrates, and where the vast majority of marine life that humans are familiar with resides. It is the zone of coral reefs, of tuna and dolphins and sea turtles, of the shimmering surface that catches light and reflects sky. Nearly all commercial fishing takes place in this zone. Nearly all recreational diving occurs within its boundaries. It is the ocean that appears in photographs, in films, in the popular imagination. It is also the thinnest layer, a bright skin stretched over an abyss. The epipelagic represents less than 3% of the ocean's total volume. Everything below it is darkness. Below 200 meters, the light begins to fail. The mesopelagic zone, sometimes called the twilight zone, stretches from 200 meters down to roughly 1,000 meters. Here, the sunlight that seemed so abundant at the surface fades into a dim, bluish glow, then into near total darkness. At the upper boundary of this zone, there may be just enough light for a human eye to detect, a faint, diffuse luminosity that provides no useful vision, but confirms that the sun still exists somewhere above. By the lower boundary, at 1,000 meters, even that faint glow is gone. The temperature drops steadily through this zone, falling from the relatively warm surface temperatures to the near-constant cold of the deep ocean. Marine life in the twilight zone is dominated by organisms that have adapted to the failing light, creatures with enormous eyes, transparent bodies, and the ability to produce their own light through bioluminescence. For every 10 meters of water above a given point, the pressure increases by approximately 1 atmosphere, the same pressure that the entire column of air from the ground to the edge of space exerts on the surface. At the bottom of the mesopelagic zone, at 1,000 meters, a body would experience roughly 100 atmospheres of pressure. That is equivalent to the weight of approximately 100 cars stacked on a single square meter of surface. A human lung, accustomed to operating at 1 atmosphere, would be compressed to 1/100th of its normal volume. The structural integrity of most human-built objects would fail long before reaching this depth. Only purpose-built submersibles and pressure vessels can survive the mesopelagic zone intact. Below the twilight zone lies the bathypelagic, the midnight zone, extending from 1,000 to 4,000 meters. No sunlight reaches here. The darkness is not the darkness of a moonless night or a closed room. It is an absolute darkness, a darkness that has never known light from above. A darkness so complete that the only illumination comes from the living things themselves, organisms that produce their own light through bioluminescence, cold chemical reactions that create brief, ghostly flashes in the void. A flash of blue from a startled squid, a glowing lure dangling from the head of an anglerfish, tiny points of green and yellow drifting through the water like stars in a liquid sky. The temperature in the bathypelagic hovers around 2 to 4 degrees Celsius, barely above freezing, and it remains this cold regardless of season, regardless of what is happening on the surface, thousands of meters above. Storms, heat waves, winters, summers, none of these reach the midnight zone. It exists in permanent, unchanging cold. The pressure here exceeds 400 atmospheres, a force sufficient to crush most submarines. Below 4,000 meters is the abyssopelagic zone, the abyssal zone, named for the Greek word for bottomless. This zone extends from 4,000 to 6,000 meters and covers the vast majority of the deep ocean floor. It is a flat, featureless plain in many places, covered in fine sediment that has been settling for immense stretches of time. This sediment is composed of the remains of countless organisms that lived and died in the waters above. Their shells, their skeletons, They're organic matter drifting slowly downward in what marine scientists call marine snow, a perpetual silent cascade of particles that settles on the abyssal floor like dust in an abandoned building. The creatures that live here have adapted to conditions that would kill almost any surface organism instantly. They survive on the sparse rain of organic matter from above, supplemented occasionally by the carcass of a whale or a large fish that sinks from the productive layers, an event so rare and so significant in the abyssal ecosystem that it has its own name, a whale fall. A single whale carcass can sustain a community of deep-sea organisms for decades, a cathedral of nutrients in an otherwise barren landscape. And then there is the Hadal Zone, named for Hades, the Greek god of the underworld. This is the deepest layer of the ocean, found only in ocean trenches, where the seabed plunges below 6,000 meters. There are approximately 33 Hadal trenches worldwide, narrow, elongated depressions in the ocean floor, where one tectonic plate is being forced beneath another. The deepest of these, the Mariana Trench, reaches approximately 10,994 meters at its deepest measured point, a location known as Challenger Deep. The pressure at Challenger Deep exceeds 1,090 atmospheres. A human body at that depth would be subjected to roughly 16,000 pounds of pressure per square inch. To give a sense of that number, imagine taking an object the size of a postage stamp and placing the weight of an entire large car upon it. Now imagine that weight applied to every square inch of the human body simultaneously. Every square inch from the crown of the head to the soles of the feet. The Hadal Zone is not merely hostile. It is a place that seems to forbid the presence of anything but the most extremely adapted life. Organisms that have evolved structures and biochemistries specifically suited to the crushing, lightless, frigid conditions of the deepest water on Earth. The Hadal Zone is also, from a human perspective, almost entirely inaccessible. The number of manned dives to Hadal depths can be counted on two hands. The total amount of time humans have spent at the very bottom of the ocean, across the entire history of deep-sea exploration, is measured in hours, not days, not weeks, but hours, brief windows of observation in an environment that resists human presence with every physical force at its disposal. By comparison, the International Space Station has been continuously occupied for more than 2 decades. The contrast is telling. Humanity has maintained a permanent presence in outer space, 350 kilometers above the surface, while the deepest waters of its own planet remain visited only in brief, fleeting expeditions. The volume of water contained within these zones is staggering. The total volume of the global ocean is estimated at approximately 1.335 billion cubic kilometers. To give that number some context, if you were to take all the fresh water on Earth, every river, every lake, every glacier, every aquifer, it would amount to less than 3% of the ocean's volume. The ocean is not just the largest body of water on the planet. It is, for all practical purposes, the only body of water on the planet, with everything else amounting to a rounding error in the total. It is within this immense volume that sound must propagate, if it is to be detected by the hydrophones that record phenomena like Upsweep. The relevance of these zones to the Upsweep mystery lies in how sound behaves within them. Sound does not travel through the ocean the way it travels through air. In air, sound moves at approximately 343 meters per second at sea level, a speed that varies slightly with temperature and humidity. In water, it moves at roughly 1,500 meters per second, a speed that varies depending on 3 critical factors: temperature, salinity, and pressure. These 3 variables create a complex acoustic landscape within the ocean, a landscape that has profound implications for how far sound can travel and how it is detected. Near the surface, where the water is warm, sound travels relatively fast. As depth increases and temperature drops, the speed of sound decreases. But below a certain point, typically around 700 to 1,000 meters, the temperature stabilizes and the increasing pressure begins to dominate, causing the speed of sound to increase again. The result is a minimum in the speed of sound at a specific depth, typically between 600 and 1,200 meters, depending on location and ocean conditions. This depth of minimum sound speed is one of the most remarkable acoustic features of the ocean, and it has a name: The SOFAR channel, which stands for sound fixing and ranging. The SOFAR channel is a horizontal layer within the ocean where the speed of sound reaches its lowest point. Above this layer, the water is warmer and sound travels faster. Below it, the pressure is greater and sound also travels faster. The result is a natural waveguide, a channel that traps sound waves and prevents them from dissipating in all directions. When a sound is generated at or near the depth of the SOFAR channel, the sound waves are continuously refracted back toward the axis of minimum velocity. Waves that begin to travel upward are bent back downward by the warmer, faster conducting water above. Waves that begin to travel downward are bent back upward by the denser, faster conducting water below. The sound bounces gently between these invisible boundaries, never escaping, never being absorbed by the surface or the seabed, propagating horizontally through the channel with extraordinary efficiency. A sound generated within the SOFAR channel can travel enormous distances, sometimes thousands of kilometers, without losing its coherence. The energy loss over these distances is extraordinarily small compared to what would occur in air or in water without the waveguide effect. In air, a sound dissipates rapidly, its energy spreading outward in all directions, absorbed by the atmosphere, weakened by distance. A shout carries perhaps a kilometer in still air. An explosion might be heard at a range of a few tens of kilometers. But in the SOFAR channel, the waveguide effect concentrates the acoustic energy, preventing it from spreading vertically, focusing it horizontally along the axis of minimum sound speed. A moderately powerful sound source at the axis of the SOFAR channel can in principle be detected on the other side of an ocean basin. This is not a theoretical abstraction. It has been demonstrated experimentally on multiple occasions. In the 1960s, researchers detonated small explosive charges at the depth of the SOFAR channel in the Indian Ocean and detected the resulting sound waves at stations in the Atlantic. Having traveled a path that curved around the southern tip of Africa, a journey of thousands of kilometers through the acoustic waveguide of the deep ocean. The signals arrived hours after the detonation, having traversed the distance at the speed of sound in water, weakened but still identifiable, still carrying the acoustic signature of the original explosion. Similar experiments were conducted in the Pacific, where explosive charges detonated near Wake Island were detected at stations near California, a distance of more than 7,000 kilometers. The results confirmed what Ewing and Wurzel had predicted. The SOFAR channel was a highway for sound, a conduit through which acoustic energy could travel the width of an ocean, with losses that seemed almost negligible compared to any other medium. The implications of this acoustic highway for the Upsweep estuary are profound. A sound detected by hydrophones in the central Pacific could have originated anywhere within the propagation range of the SOFAR channel. The source could be thousands of kilometers from the nearest sensor. The multilateration techniques used to estimate source location have inherent uncertainties that grow with distance, meaning that the estimated source coordinates for Upsweep are approximate, not precise. The sound could originate from a point that is tens or even hundreds of kilometers from the estimated location, and this uncertainty alone is enough to encompass a vast area of unexplored seabed. The SOFAR channel was first described in the late 1940s by Maurice Ewing and J. Lamar Wurzel at Columbia University. Their research demonstrated that low-frequency sounds could propagate across entire ocean basins with extraordinarily little loss of energy. Ewing was a physicist and geophysicist whose career spanned some of the most transformative discoveries in ocean science. He recognized immediately that the SOFAR channel had profound implications, not only for scientific research, but for military applications. If a downed pilot or a sinking ship could deploy a small explosive charge at the depth of the SOFAR channel, the resulting sound could be detected by listening stations thousands of kilometers away, providing a means of locating survivors in the vastness of the open ocean. This principle was tested and validated, and it became one of the foundations of underwater acoustic research. The military implications of the SOFAR channel led directly to the development of the sound surveillance system, known by its acronym SOSUS, a network of hydrophone arrays deployed on the ocean floor by the United States Navy during the Cold War. SOSUS was one of the most ambitious and secretive acoustic projects in military history. Beginning in the early 1950s, the Navy installed arrays of hydrophones at strategic locations along the continental shelves of the Atlantic and Pacific Oceans. These arrays were connected to shore-based processing centers by undersea cables that stretched for hundreds of kilometers, and their primary purpose was to detect and track Soviet submarines. The sensitivity of the SOSUS system was extraordinary. The hydrophones were positioned at or near the depth of the SOFAR channel, maximizing their ability to detect low-frequency sounds propagating through the waveguide. SOSUS could detect the low-frequency sounds produced by submarine propulsion systems at ranges of hundreds or even thousands of kilometers. It could distinguish between different classes of submarines based on the unique acoustic signatures of their machinery. A Typhoon-class ballistic missile submarine sounded different from a Victor-class attack submarine, and the analysts at the SOSUS processing centers could identify these differences in real time, tracking the movements of the Soviet submarine fleet across the ocean basins with a precision that was among the most closely guarded secrets of the Cold War. For decades, the existence and capabilities of SOSUS were classified. The system operated in secret, its listening stations manned by naval personnel who understood the significance of their work but could not discuss it publicly. The data flowing into the processing centers was analyzed, catalogued, and used to build a continuously updated picture of Soviet submarine movements, a picture that informed naval strategy and nuclear deterrence planning at the highest levels of government. When the Cold War ended, the strategic necessity of SOSUS diminished. The Soviet submarine fleet contracted, the immediate threat of nuclear war receded, and portions of the SOSUS system were made available for scientific research, one of the most remarkable transfers of military technology to civilian science in modern history. In the early 1990s, the National Oceanic and Atmospheric Administration, NOAA, gained access to the hydrophone data and began deploying its own autonomous underwater hydrophone arrays, extending the listening capability into remote regions of the Pacific that had been beyond the reach of the original SOSUS network. The Pacific Marine Environmental Laboratory, a division of NOAA based in Newport, Oregon, became the primary institution responsible for analyzing the hydrophone data. The laboratory's acoustic monitoring program was initially focused on detecting and cataloging submarine volcanic activity and seismic events in the deep ocean. The hydrophones were deployed at locations optimized for capturing low-frequency sounds propagating through the SOFAR channel, and they recorded continuously, around the clock, every day of the year, day, producing vast archives of acoustic data that scientists would sift through in search of signals. It was within these archives that the anomalies began to appear. Sounds that did not match the known signatures of earthquakes, volcanoes, ships, or marine life. Sounds with characteristics that defied easy categorization. Sounds that repeated with a regularity, suggesting a persistent source rather than a random event. The scientists at the Pacific Marine Environmental Laboratory were accustomed to identifying the acoustic signatures of natural phenomena. They could recognize an earthquake by its low-frequency rumble and its characteristic duration. They could identify a volcanic eruption by its explosive onset and its harmonic tremor. They could distinguish between the calls of different whale species by their frequency, rhythm, and spectral structure. But these new sounds fit none of those categories. They were something else. The scientific community would eventually identify and name several of these anomalous signals, each with its own distinctive waveform and its own set of unanswered questions. There was the bloop, a powerful ultra-low frequency sound detected in 1997. There was slow down, a sound that gradually decreased in frequency over approximately 7 minutes. There was Julia, named for its resemblance to a human voice when compressed in time and shifted to audible frequencies. There was the train, a low-frequency rumble reminiscent of distant machinery. There was the whistle, a brief ascending tone. And there was Upsweep, the oldest of them all, the one that had been there from the very beginning of the recording program, the one that had never stopped. The transition from military to civilian use was not without its challenges. The SOSUS infrastructure was designed for submarine detection, not for environmental monitoring. The frequency ranges of interest were different. The analytical methods were different. The questions being asked were different. But the fundamental capability, the ability to listen to the ocean at low frequencies over vast distances, was exactly what scientists needed to study the acoustic environment of the deep sea. And the data that poured in from the repurposed arrays and the newly deployed autonomous hydrophones was richer than anyone had anticipated. The ocean was far noisier, far more acoustically complex, and far more mysterious than the military applications of SOSUS had suggested. The autonomous hydrophones deployed by NOAA in the early 1990s were a crucial complement to the SOSUS arrays. These instruments were self-contained units, anchored to the seabed at depths near the SOFAR channel, recording continuously onto internal storage media that would be retrieved periodically by research vessels. Their locations were chosen to extend coverage into areas of the Pacific that the original SOSUS network had not reached, particularly the eastern and southern Pacific, where volcanic and seismic activity along the mid-ocean ridge system was of particular scientific interest. The acoustic data recorded by these instruments revealed a deep ocean that was anything but quiet. The low-frequency ambient sound of the ocean is a constant, complex mixture of signals from dozens of sources. Earthquakes generate rumbles that propagate for thousands of kilometers. Volcanic activity produces harmonic tremor and explosive bursts. Marine mammals, particularly the great whales, fill the deep ocean with calls that can be detected across entire basins. Ships generate a constant hum of engine noise and propeller cavitation that has steadily increased over the decades, raising the baseline noise level of the ocean and potentially interfering with the ability of marine animals to communicate. Wind-driven waves create a broadband noise that extends from the surface deep into the water column. And beneath all of these sounds, like a rhythm section beneath a melody, there is the constant, subtle vibration of the ocean floor itself, driven by the interaction of ocean waves with the seabed, a phenomenon known as ocean microsysm. Against this backdrop of identified sounds, the anomalous signals stood out. They were unusual not because they were loud, though some were powerful, but because their characteristics did not match any known source. Their spectral shapes were unfamiliar. Their durations were unexpected. Their locations, when they could be estimated, were in remote, uninhabited regions of the ocean, far from any human activity. They were the acoustic equivalent of finding a word in a foreign language, embedded in a text you otherwise understand completely, recognizable as a signal, clearly distinct from noise, but impossible to translate. The foundation for understanding Upsweep is built on 3 pillars. The first is the sheer scale of the ocean, a volume of water so enormous that it can contain sounds of unknown origin without yielding their source, a space so vast that the distance between a sound and the instrument that records it can span the width of an entire ocean basin. The second is the physics of underwater sound propagation, particularly the SOFAR channel, which allows signals to travel vast distances and be detected far from their point of origin, which means that a sound recorded in the central Pacific may have originated anywhere within thousands of kilometers of the hydrophone that captured it. The third is the history of ocean acoustic monitoring, a history rooted in Cold War secrecy, in billion-dollar military investments, and in a geopolitical tension that, when it relaxed, released some of the most powerful listening technology ever built into the hands of civilian scientists. Each of these pillars reveals something about the limitations of human knowledge. The ocean is not a transparent medium. It does not yield its secrets to visual inspection. Below the epipelagic zone, it is a world of darkness, accessible only through sound, through instruments, through the indirect evidence of pressure waves moving through water. When those pressure waves carry a signal that cannot be identified, scientists are left with a puzzle that has no visual component, no physical specimen to examine, no experiment that can be easily replicated in a laboratory. They have only the waveform, the spectrogram, the frequency and amplitude and duration of a sound that may have traveled thousands of kilometers before reaching the hydrophone that recorded it. The technology that detects these sounds is extraordinary, the product of decades of engineering and enormous investment. But the ocean that contains them is more extraordinary still. It is a space where sound can persist for hours, where a single event can be heard across an entire basin, where the properties of water itself create conditions that have no analogue on land. On the surface, sound is fleeting. A word spoken dissipates within moments, its energy absorbed by the air and the surroundings. In the deep ocean, sound is enduring. A signal entering the SOFAR channel can travel for hours, maintaining its structure and identity across distances that would render any surface sound inaudible. The deep ocean remembers its sounds in a way that no terrestrial environment does. In this space, a sound like upsweep could originate from a source thousands of kilometers from the nearest hydrophone and still arrive with enough clarity to be analyzed and catalogued. The distance between detection and understanding is vast, and it is into that distance that the mystery of upsweep disappears, a sound heard clearly but explained only uncertainly, a signal that the ocean delivers to the instruments and then declines to explain. The hydrophones have done their job. They have captured the sound with precision and fidelity. But the ocean has done what it always does. It has concealed the source, hidden it behind thousands of meters of water and thousands of kilometers of distance, daring anyone with the curiosity and the resources to come looking. The listening stations heard something. They have been hearing it for decades. And the question that has persisted through all those years of recording, all those spectrograms and frequency analyses and scientific papers, is a question that should trouble anyone who believes humanity has mastered its understanding of this planet. What exactly is making that sound, and why has it not stopped? The upsweep sound was first identified in August of 1991, when researchers at NOAA's Pacific Marine Environmental Laboratory began reviewing data from their hydrophone arrays deployed in the equatorial Pacific Ocean. The arrays had been positioned to capture acoustic signals propagating through the SOFAR channel, and the data they returned was dense, complex, and full of signals requiring classification. Among the recordings of distant earthquakes, the groans of tectonic plates shifting, and the calls of marine mammals, there was something else, a sound that climbed. A sound that rose in frequency over a period of several seconds, paused briefly as if catching its breath, and then began again. It was not particularly dramatic when isolated from its context. It was not the loudest sound in the data, nor the most complex, but it was persistent and it was unfamiliar, and when the researchers compared it against the catalogue of known ocean sounds, it matched nothing. The researchers who first isolated the signal described it as a narrowband upsweeping tone. In acoustic terms, narrowband means that the sound was concentrated within a relatively small range of frequencies, as opposed to broadband sounds like explosions or crashing waves that spread their energy across a wide spectrum. The upsweeping characteristic was the defining feature, a steady rise in pitch from a lower frequency to a higher one, creating a waveform on a spectrogram that appeared as a series of ascending lines, parallel streaks angled upward from left to right, each one representing a single instance of the sweep. Each individual sweep lasted several seconds, and the sweeps repeated in a semi-regular pattern, producing a continuous train of ascending tones that persisted for extended periods. On a spectrogram, the pattern was distinctive and immediately recognizable, unlike the horizontal lines of continuous tones or the vertical spikes of impulsive sounds. Upsweep had its own visual signature, as unmistakable to a trained analyst as a fingerprint. The process of identifying and classifying ocean sounds is, in many ways, similar to the work of a detective. The acoustic analyst begins with a recording, a raw trace of pressure variations over time. This trace is then transformed into a spectrogram, a visual representation that plots time along one axis and frequency along another, with the intensity of the sound indicated by color or brightness. A spectrogram turns sound into something that can be seen, and the trained eye can read a spectrogram the way a musician reads sheet music, recognizing patterns, identifying signatures, and distinguishing between known sounds and unfamiliar ones. When the NOAA analysts first examined the spectrograms containing the upsweep signal, the pattern was immediately apparent. The ascending lines were distinct from the background noise, clear and repeating, standing out against the murky wash of ocean ambient sound, the way a bird's call stands out against the background rustle of a forest. The analysts checked the signal against their reference catalogues, the collections of known acoustic signatures that had been built up over decades of military and scientific monitoring. They compared it to the signatures of known whale calls, known seismic signals, known volcanic signatures, known ship noise, known ice sounds. It matched nothing. The sound was new. The process of checking a new signal against the catalogue of known sounds is exhaustive and time-consuming. Each potential source must be considered individually. Could this be a blue whale call distorted by propagation effects? No, because the spectral characteristics are wrong, the frequency range is different, and the pattern does not match any known call type. Could this be harmonic tremor from a known volcanic source? No, because the location does not correspond to any known eruption and the ascending pattern is unlike typical tremor signatures. Could this be noise from a ship's propulsion system? No, because no shipping lane passes through the estimated source region, and the spectral characteristics are unlike any known vessel. Each possibility is evaluated, and each is ruled out, until the analyst is left with the conclusion that the sound does not correspond to any known source. It is, by the standard definition, unidentified. What made the initial detection notable was not merely the sound itself, but its ubiquity. The upsweep signal was not a brief event captured by a single hydrophone at a single moment in time. It was detected by multiple hydrophones across the Pacific simultaneously. The signal appeared on recordings from sensors separated by thousands of kilometers, each one receiving the same ascending tone at slightly different times, the differences corresponding to the time it took for the sound to travel from the source to each sensor through the SOFAR channel. Whatever was producing the sound was either extraordinarily loud, allowing it to propagate across an entire ocean basin, or there were multiple sources distributed across a wide area, or the SOFAR channel was carrying a single source signal with such efficiency that it could be heard at ranges that would be impossible in any other medium. Each of these possibilities was considered. Each had implications that were difficult to reconcile with known phenomena. The source location was estimated through a process called multilateration, which involves comparing the arrival times of the same signal at different hydrophone positions. By measuring the tiny differences in when the sound reached each sensor, researchers could triangulate the approximate origin point, much as a person can estimate the direction of a sound by noting which ear hears it first. With multiple sensors spread across the Pacific, the triangulation could be narrowed to a region, though not to a precise point. The initial analysis placed the source of upsweep in the remote southern Pacific Ocean, near the coordinates of approximately 54 degrees south latitude and 140 degrees west longitude. This location is in one of the most isolated stretches of ocean on Earth. The nearest major landmass is New Zealand, more than 5,000 kilometers to the west. South America lies thousands of kilometers to the east. Antarctica stretches across the horizon to the south. The region is far from any shipping lanes, far from any permanent human habitation, far from any research station or port facility. It is a part of the ocean that few humans have ever visited, and fewer still have studied in any depth. The waters are deep, the weather is brutal, and the distances involved in reaching the area from any research base are measured in weeks of ship travel. To appreciate the remoteness of this location, consider that it lies within the general vicinity of what mariners and geographers have sometimes called the oceanic pole of inaccessibility, the point in the ocean that is farthest from any land in all directions. This point, located in the South Pacific, is sometimes referred to by its informal name, Point Nemo, after the fictional submarine captain. The area surrounding Point Nemo is so remote that when a spacecraft is deorbited, space agencies often aim it at this region, on the reasoning that the chances of striking a ship or a person are effectively zero. The nearest humans to Point Nemo at any given moment are often the astronauts aboard the International Space Station, passing overhead at an altitude of roughly 400 kilometers. The upsweep source lies in this same general region of extreme oceanic isolation, a location where the nearest help, the nearest port, the nearest research vessel could be weeks away. The remoteness of the source location is not merely an inconvenience for scientists, it is a fundamental obstacle to understanding. In science, hypotheses are tested through observation and experiment. A hypothesis about the source of a sound requires that someone go to the location of the sound, deploy instruments, and observe what is happening. When the location is easily accessible, this process is straightforward. When the location is one of the most remote places on Earth, surrounded by some of the roughest seas in the world, at depth of several thousand meters, the process becomes extraordinarily difficult, dangerous, and expensive. The remoteness of the upsweep source is not incidental to the mystery. It is central to it. The sound is unexplained in large part because the place from which it originates has never been directly investigated. If the upsweep source were located off the coast of California or in the well-studied waters of the North Atlantic, it would almost certainly have been identified by now. The instruments, the expertise, and the infrastructure exist. What is missing is proximity. The ocean has placed its mystery in the one place where answering it is hardest. The nearest significant geological feature to the estimated source location is the Pacific-Antarctic Ridge, a section of the global mid-ocean ridge system, where tectonic plates are spreading apart, and new ocean floor is being created through volcanic activity. The mid-ocean ridge system is the largest geological feature on Earth, a continuous chain of volcanic mountains that runs through every ocean basin like the seam on a baseball, stretching more than 65,000 kilometers from the Arctic to the Antarctic, through the Atlantic, the Indian Ocean, and the Pacific. Along its entire length, magma rises from deep within the Earth's interior, filling the gap between separating plates and creating new oceanic crust, in a process that has been ongoing for as long as the plates have been moving. The correlation between the estimated source location of Upsweep and the Pacific-Antarctic Ridge was immediately significant. Mid-ocean ridges are among the most geologically active features on the planet. They are zones where magma rises from beneath the Earth's crust, creating new oceanic crust as tectonic plates move apart at rates of a few centimeters per year. This process is accompanied by intense volcanic and hydrothermal activity. Hot magma, at temperatures exceeding 1000 degrees Celsius, interacts with cold seawater at temperatures near freezing, producing a range of physical and chemical reactions that generate enormous amounts of energy. Earthquakes along the ridge generate low-frequency rumbles as rocks fracture and shift. Volcanic eruptions produce explosive sounds as magma breaks through the crust and encounters seawater. Hydrothermal vents, where superheated water erupts from the seabed at temperatures exceeding 350 degrees Celsius, create sustained noise as water and dissolved minerals are ejected into the surrounding ocean. The acoustic output of a mid-ocean ridge is complex, varied, and continuous, a constant soundtrack of geological activity that fills the surrounding water with signals. The initial hypothesis, and one that remains the most widely cited, was that upsweep was being generated by volcanic or hydrothermal activity on or near the Pacific-Antarctic Ridge. This was a reasonable deduction based on the available evidence. The location matched. The persistence of the sound was consistent with an ongoing geological process rather than a single event, and there was a known mechanism by which volcanic activity could produce ascending tones, specifically the interaction between magma and seawater in confined geological structures. When magma comes into contact with seawater, the water is superheated almost instantaneously, producing steam. If this steam is generated within a confined space, such as a lava tube, a fracture in the rock, or a partially enclosed magma chamber with an opening to the ocean, it can create resonant oscillations, vibrations that occur at specific frequencies determined by the geometry of the confining space. As the steam rises and the geometry of the system changes, as the confining space expands or contracts, as the temperature and pressure within the cavity shift, the frequency of these oscillations can change. potentially producing the ascending tone characteristic of upsweep. This mechanism is well documented in the study of volcanic activity on land, where the interaction between water and magma in confined conduits can produce harmonic tremor, a sustained, quasi-periodic signal that is a hallmark of many volcanic eruptions. Volcanologists have recorded similar ascending tones from fumaroles and lava tubes on land, where the physics of resonant oscillation in confined spaces is well understood. But here is the problem. The volcanic hypothesis, while plausible on paper, has never been confirmed through direct observation. No expedition has visited the precise source location to observe the mechanism in action. No camera has recorded the geological feature responsible for the sound. No instrument has been placed on the seabed at the estimated coordinates to measure the local acoustic environment. The Pacific-Antarctic ridge, in the vicinity of the estimated source coordinates, is one of the least explored sections of the mid-ocean ridge system, lying in remote, stormy waters of the Southern Ocean, thousands of kilometers from the nearest port, far from the research infrastructure that supports most deep-sea exploration. The depth of the water in that region, combined with the extreme distance from facilities, the hostile sea conditions, and the expense involved, makes any direct investigation extraordinarily difficult and prohibitively costly. And it gets worse. The upsweep signal has characteristics that do not perfectly match a simple volcanic or hydrothermal origin. One of the most puzzling aspects of the sound is its seasonal variation. Analysis of the long-term recording data has revealed that upsweep is not constant in amplitude throughout the year. It is strongest in spring and autumn, the equinoctial seasons, and weakest in summer and winter, the solstitial seasons. This seasonal pattern has been consistent across multiple years of recording, appearing year after year with a regularity that suggests the phenomenon is influenced by factors that vary on an annual cycle. The pattern is not subtle. The difference in amplitude between the strongest and weakest periods is large enough to be clearly visible in the long-term data, a rhythmic waxing and waning that overlays the persistent ascending tone like a slow seasonal pulse. Volcanic activity on the mid-ocean ridges does not typically exhibit seasonal variation. The movement of tectonic plates, the rise of magma from the mantle, the eruption of lava onto the seabed, these are processes driven by forces deep within the Earth's interior, forces that operate on timescales of thousands or millions of years, forces that are entirely indifferent to the tilt of the Earth's axis and the resulting progression of seasons at the surface. The temperature of the water at the depth of the mid-ocean ridges does not change with the seasons. The pressure does not change. The rate of magma production does not vary from summer to winter. There is no known mechanism by which the output of a deep-sea volcanic system would increase in spring and autumn and decrease in summer and winter. The volcanic hypothesis, applied straightforwardly, predicts a constant or slowly varying signal, not a seasonally modulated one. One proposed explanation for the seasonal variation involves the interaction between surface conditions and the acoustic propagation path. The SOFAR channel, the waveguide through which the sound travels, is influenced by the temperature and salinity profiles of the water column. These profiles change with the seasons, particularly in the upper ocean, where surface heating in summer and cooling in winter alter the thermal structure of the water. In spring and autumn, the rapid changes in surface temperature create conditions in the upper ocean that can affect the efficiency of the SOFAR channel, potentially altering how well it transmits certain frequencies. It is possible that the seasonal variation in upsweep's amplitude is not a change in the source itself, but a change in the acoustic highway through which the sound travels, an illusion created by the shifting properties of the ocean water. This explanation has the virtue of not requiring any seasonal variation in the volcanic source itself. It shifts the seasonal effect from the emitter to the medium, from the thing making the sound to the water carrying it. But it is difficult to verify. The mathematical models that describe sound propagation through the SOFAR channel are complex, involving dozens of variables that change with location, depth, and time. Modeling the seasonal effect on a specific acoustic path from the southern Pacific to the hydrophone locations in the central and eastern Pacific requires detailed knowledge of the temperature and salinity profiles along the entire propagation path, knowledge that is only available in fragmentary form for such remote waters. Oceanographic measurements in the southern Pacific are sparse. Research vessels transit the region infrequently. The temperature and salinity data that exists comes primarily from satellite observations and from a network of autonomous profiling floats called Argo, which measure conditions in the upper 2,000 meters of the ocean. Below that depth, and particularly along the complex acoustic paths that the upsweep signal might follow through the SOFAR channel, the data becomes thin. The models that have been constructed using this limited data suggest that seasonal changes in the SOFAR channel could produce some variation in received signal amplitude, but they have not been able to fully reproduce the magnitude or the exact timing of the observed variation. The discrepancy is not enormous, but it is persistent, appearing in model after model, analysis after analysis. The seasonal mystery remains an open question, a wrinkle in the volcanic hypothesis that has not been ironed out despite decades of analysis. It is possible that the models are simply not accurate enough, that with better data from the propagation path, the seasonal variation could be fully explained by propagation effects. But it is also possible that the seasonal variation is real, that the source itself varies with the seasons, and that this variation reflects a mechanism more complex than simple volcanic activity. Another puzzling characteristic of Upsweep is its gradual decline in amplitude over the decades since its first detection. The sound was loudest in the early 1990s, when it was first recorded, and has been slowly growing quieter year by year since then. This decline has been documented in the long-term monitoring data and is consistent across multiple hydrophone stations, ruling out the possibility that it is an artifact of a single sensor degrading over time. The trend is unmistakable. Whatever is producing Upsweep is producing it less powerfully now than it was 30 years ago. The decline is gradual, not sudden. There is no evidence of a step change, no moment when the amplitude dropped sharply. Instead, the signal has been fading slowly, like a light dimming so gradually that you only notice the change when you compare the present to the past. If the source is volcanic, this decline could indicate a gradual reduction in the activity producing the sound. Perhaps a magma body is cooling, its thermal energy dissipating into the surrounding rock and water, reducing the vigor of the interactions that generate the sound. Perhaps a conduit is narrowing as mineral deposits accumulate along its walls, constricting the flow of steam or water that drives the resonance. Perhaps a volcanic episode that began before the hydrophones were deployed is slowly winding down, its energy dissipating over decades in a pattern that is well documented in the study of terrestrial volcanoes, where periods of elevated activity can last for years or decades before the system returns to quiescence. The Kilauea volcano in Hawaii, for example, sustained an eruption for more than 35 years before entering a period of reduced activity. Volcanic systems operate on their own timescales, and a decades-long decline is not unusual. This interpretation is consistent with the known behavior of volcanic systems, but it is also possible that the decline indicates something else entirely. A change in the resonant properties of the source structure, a shift in the propagation conditions along the acoustic path, or a gradual alteration in the mechanism that generates the sound. Without direct observation of the source, the cause of the decline remains as uncertain as the source itself. The spectral characteristics of Upsweep have been studied in extraordinary detail by researchers at NOAA and at universities around the world. The sound consists of a series of narrowband tones that sweep upward in frequency, typically ranging from very low frequencies below 1 Hz up to several Hz. The precise frequency range and sweep rate vary over time, but the basic pattern is consistent, a characteristic rising tone that repeats with mechanical regularity. The tones are pure, meaning they are concentrated at specific frequencies rather than spread across a broad spectrum. This spectral purity is significant because it strongly suggests a resonant mechanism, a system that vibrates at preferred frequencies determined by its physical properties, rather than a chaotic or random process that would produce broadband noise. The purity of the tones means that whatever is producing the sound has a defined physical structure, a geometry, that selects for certain frequencies and suppresses others, in the same way that a pipe organ produces specific notes, because the dimensions of each pipe determine the wavelengths at which air vibrates most efficiently. Resonance systems in the natural world are well understood in general terms. A struck bell produces specific frequencies because the geometry and material of the bell define its natural modes of vibration. A wind blowing across the mouth of a bottle produces a tone determined by the volume of the bottle and the size of the opening. A river flowing through a narrow canyon can produce sustained tones as the air trapped inside channels vibrates at resonant frequencies. In the ocean, resonant tones can be produced by the interaction of water and rock in confined spaces, by the oscillation of gas bubbles in magma or in the water column, or by the vibration of fluid-filled cavities in the seabed. Each of these mechanisms has been proposed as a possible explanation for the spectral characteristics of upsweep, and each has been found to have limitations that prevent it from serving as a complete explanation. The bubble oscillation hypothesis suggests that large bubbles of volcanic gas, released from magma at depth, could oscillate as they rise through the water column. The natural frequency of a gas bubble in water depends on its size. A small bubble oscillates at a higher frequency than a large one. As a bubble rises through the water and the surrounding pressure decreases, the bubble expands, changing its natural frequency. This change in frequency, as the bubble rises, could, in principle, produce an ascending tone. However, the relationship between bubble size, depth, and frequency does not perfectly match the observed characteristics of upsweep. The rate at which the frequency ascends, the duration of each sweep, and the regularity of the pattern all present challenges for the bubble model. Natural bubble release from a volcanic source would be expected to produce variable, somewhat random signals, the regular, repeating pattern that characterizes upsweep. The model works in broad outline but fails in the details. The fluid-filled cavity hypothesis proposes that seawater entering a cavity in the volcanic rock, perhaps a collapsed lava tube, a magma chamber with an opening to the ocean, or a network of interconnected fissures, could create resonant oscillations as the cavity fills and drains with the rhythm of deep ocean currents, tidal movements, or pressure variations. The dimensions of the cavity would determine the natural frequencies of the oscillation, and if the cavity had a geometry that changed along its length, such as a tapered tube or a chamber with a narrowing outlet, the oscillation could produce a tone that sweeps upward in frequency as the system moves through different modes of vibration. This hypothesis is appealing because it can potentially explain both the spectral purity of the signal, which would arise from the resonant properties of the cavity, and the ascending frequency pattern, which would arise from the changing geometry or filling state of the cavity. It could even, in some formulations, explain the seasonal variation if the deep ocean currents or tidal forces that drive the filling and draining of the cavity vary with the seasons. But the fluid-filled cavity hypothesis is exactly that, a hypothesis. No specific cavity or geological structure has been identified at the estimated source location that matches the required dimensions. The hypothesis makes specific, testable predictions about the physical environment at the source. A cavity of a certain size and shape must exist. It must be connected to the ocean through an opening of a certain dimension. It must be located at a depth and in a geological context that allows it to resonate at the observed frequencies. These predictions could be tested through direct survey of the seabed, through high-resolution sonar mapping, through the deployment of cameras and instruments on the ocean floor, but no such survey has been conducted. The southern Pacific is simply too remote, too deep, too hostile, and too expensive to explore with the thoroughness that would be needed to locate a specific resonant feature on a specific section of mid-ocean ridge. But here's the problem. The challenge of explaining upsweeps is compounded by the extraordinary difficulty of studying any phenomenon in the deep ocean. On land, when a mysterious sound is reported, scientists can travel to the location, set up instruments, observe the environment, and search for the source. The distance between detection and investigation is measured in hours or days. In the deep ocean, that distance is measured in months of preparation, Weeks of ship travel, millions of dollars of equipment deployment, and often years of analysis before results are published. A researcher who suspects that a particular section of the Pacific-Antarctic ridge might contain the source of Upsweep cannot simply go there and look. The expedition would need to be planned years in advance. A research vessel capable of operating in the Southern Ocean would need to be secured, a process that involves navigating institutional bureaucracies, securing funding from competitive grant programs, and coordinating with other research priorities. The instruments needed for a deep-sea survey, including multi-beam sonar, remotely operated vehicles, and autonomous underwater vehicles, would need to be allocated and prepared. The total cost of such an expedition could easily exceed $10 million, a figure that must be justified against competing scientific priorities. The result is a frustrating asymmetry. Scientists have detailed information about what the upsweep sound is, its frequency characteristics, its amplitude, its duration, its seasonal variation, its long-term trends. They have this information because the hydrophones record continuously and the data is analyzed systematically. But they have almost no information about the physical environment where the sound originates. They cannot see the source. They cannot measure the local conditions. They cannot test the hypotheses about volcanic conduits, resonant cavities, or bubble oscillation against direct physical evidence. It is as if someone were asked to identify a musical instrument based solely on a recording of a single note, played from behind a wall that cannot be breached, in a room that cannot be entered, at a location that cannot be easily reached. The recording is superb, the analysis is meticulous, but the instrument remains hidden. The history of ocean acoustics offers some comfort. It is full of sounds that were initially mysterious and later explained through patient investigation. The biological origin of certain low-frequency sounds in the ocean was unknown for decades. In the 1950s and 60s, Navy analysts monitoring SOSUS recordings detected repetitive, low-frequency pulses that they could not attribute to any known submarine or mechanical source. These signals were eventually identified as the calls of fin whales and blue whales, animals so large that their vocalizations operate at frequencies near the lower limit of human hearing. The identification required years of work, correlating acoustic recordings with visual surveys of whale populations, deploying hydrophones near known feeding and breeding grounds, and building a catalogue of whale calls that could be matched against the unidentified signals. The process was slow and painstaking, but it ultimately succeeded, transforming mysterious ocean sounds into one of the most powerful tools for studying whale behavior and distribution. Similarly, a persistent low-frequency hum detected in the deep ocean was debated for years before it was attributed to the interaction of ocean waves with the seabed, a phenomenon known as ocean microsysm. This constant vibration, which permeates the entire ocean at frequencies below 1 Hz, is generated by the interaction of opposing ocean swells and their coupling with the solid Earth. Understanding this required advances in both ocean acoustics and seismology, as the phenomenon exists at the boundary between the two fields. The explanation, when it came, was elegant and satisfying, revealing a fundamental connection between the movement of the ocean's surface and the vibration of the Earth's crust beneath it. In each case, the explanation came through a combination of improved instrumentation, direct observation, and the gradual accumulation of evidence over many years of patient, systematic investigation. The pattern is consistent. Ocean sounds that initially seem mysterious are eventually explained, not through sudden breakthroughs, but through the slow, steady work of scientists who are willing to spend years or decades pursuing an answer. Upsweep may eventually follow the same path. Its source may be confirmed by an expedition that visits the right stretch of ridge at the right time with the right instruments. The volcanic conduit hypothesis may be vindicated by the discovery of a specific geological feature that matches the required dimensions and produces the observed acoustic signature. Or the explanation may turn out to be something entirely different, something that has not yet been considered, something that will seem obvious in retrospect, but that is currently hidden behind the veil of distance, depth, and ignorance. But more than 3 decades have passed since the sound was first detected, The data has accumulated. The papers have been published. The hypotheses have been proposed and debated and found wanting. And the sound continues, rising through the deep Pacific, with the same patient regularity it had when it was first recorded, indifferent to the questions it provokes, indifferent to the debates it inspires, indifferent to the entire human enterprise of trying to understand it. Something in the deep southern Pacific has been producing a distinctive ascending tone for more than 30 years. That tone has been heard across the entire Pacific basin by the most sensitive listening equipment ever deployed. The best hypothesis points to volcanic or hydrothermal activity on the Pacific-Antarctic ridge, but this hypothesis has never been directly confirmed, and it cannot fully explain the seasonal variation in the sound's amplitude or the precise spectral characteristics of the signal. The sound has been declining in amplitude, growing gradually quieter, suggesting a source that may be slowly winding down, but the timeline and rate of decline do not match any well-documented volcanic process with precision. The upsweep sound is not loud in the way a human voice is loud. It exists in the deep infrasonic range, at frequencies below the threshold of human hearing. If you were in the water at the source location, you would not hear it with your ears. You might feel it, a vibration in the water, a subtle pressure fluctuation against your body, but the frequency is too low for the human auditory system to process as sound. Human hearing ranges from approximately 20 Hz to 20,000 Hz. Upsweep operates below that lower boundary, in the realm of infrasound, where vibrations are felt rather than heard, where the boundary between sound and physical sensation blurs. Played back at increased speed and shifted into the audible range, a technique that compresses hours of recording into seconds and raises the frequency into the range of human perception, the upsweep sound takes on an eerie, almost musical quality. It sounds like a rhythmic climbing tone that repeats with mechanical regularity, like a breathing machine in a hospital, or a siren heard from very far away, or something pulling itself upward through the water, one step at a time. The ascending pattern is unmistakable, a deliberate sounding rise that peaks and then begins again from the bottom, over and over, with a patience that seems almost intentional. Hearing it provokes a visceral sense that something purposeful is happening, that the ascending pattern reflects design rather than random geological noise. This impression is misleading, of course. Natural systems are perfectly capable of producing regular, pattern sounds without any intention behind them. The wind whistling through a crack in a wall sounds deliberate, but is not. The rhythmic dripping of water in a cave sounds intentional, but is not. A geyser erupting on schedule sounds purposeful, but is merely the result of predictable thermodynamic cycles. But the impression lingers because human brains are wired to detect patterns and to attribute meaning to them, and the ascending pattern of upsweep is so regular, so consistent, so repeatable that it engages the pattern recognition systems of the human mind in a way that random noise never would. It is part of what has kept public fascination with upsweep alive for more than 3 decades, this sense that the sound means something, even if the meaning cannot be determined. The public fascination with upsweep and the other unidentified ocean sounds has at times outpaced the science. The internet age brought these sounds to a global audience, as NOAA published audio clips and spectrograms that could be downloaded and shared. Online forums and social media amplified the mystery, with speculation ranging from the plausible to the fantastical. Some suggested that the sounds were evidence of undiscovered marine megafauna, enormous creatures lurking in the deep ocean, a modern equivalent of the sea monsters that populated medieval maps. Others connected the sounds to fringe theories about underwater civilizations, alien communication, or secret military experiments. These speculative interpretations, while engaging for a popular audience, bear no relationship to the scientific evidence and have been consistently rejected by the research community. The actual scientific investigation of upsweep has been careful, methodical, and appropriately cautious. Researchers have published peer-reviewed analyses of the signal's characteristics, proposed and tested hypotheses against the available data, and acknowledged openly when those hypotheses fall short of a complete explanation. The scientific process, when applied to a phenomenon as elusive as upsweep, is necessarily slow. Each new analysis builds on the previous one, refining the understanding incrementally, narrowing the range of possibilities, without eliminating them entirely. This incremental progress can be frustrating for those who want a definitive answer, but it reflects the honest state of knowledge. The scientists studying upsweep do not claim to have solved it. They claim to have constrained the possibilities, and they are forthright about the constraints that remain. The scientific community has not declared the upsweep mystery solved. NOAA's records continue to list it among the unidentified sounds detected by its hydrophone program. Research papers published over the years have offered analyses and hypotheses, but none has achieved the status of a definitive, universally accepted explanation. The sound remains in a category that scientists find deeply uncomfortable, a well-documented, well-characterized signal from a persistent source, recorded by reliable instruments, analyzed by competent researchers, and still not conclusively identified. It sits in the scientific record as an open case, a file that has never been closed, a question that has never received a final answer. The hydrophones continue to record, the data continues to accumulate, and the sound continues to rise, year after year, sweep after sweep, a patient ascending tone that asks nothing of the scientists who study it and answers nothing in return. The upsweep sound is not the only mystery in the deep ocean. It is one of many, but its persistence, its duration, its sheer stubbornness in resisting explanation sets it apart from the others. Most unidentified sounds are transient. They appear, they are recorded, they vanish. Upsweep appeared and stayed. It has been there for the entire history of modern ocean acoustic monitoring. It may have been there long before, and its continued presence raises questions that go beyond the identity of a single sound. Questions about the state of human knowledge, about the completeness of the maps and models that claim to describe this planet, about the vast, dark, unexplored spaces that lie beneath the surface of the sea. But here is what makes this truly terrifying. The ocean floor is a landscape of extremes, and the features that dot the deep Pacific are among the most otherworldly environments on this planet. To understand why a sound like upsweep resists explanation, it helps to examine the broader catalogue of deep-sea mysteries that have challenged scientific understanding, the phenomena that exist at the boundaries of the known world, where familiar physics operates in unfamiliar ways, and the assumptions built on surface experience break down. Each of these phenomena reveals something about the limitations of current knowledge, and each demonstrates, in its own way, how much the ocean conceals from the species that lives on its surface. The first and most obvious avenue of investigation for upsweep leads to the hydrothermal vents of the mid-ocean ridges. These vents, first discovered in 1977 during an expedition aboard the research submersible Alvin near the Galapagos Rift, are openings in the seabed where superheated water, rich in dissolved minerals, erupts into the surrounding ocean. The discovery was made by a team of geologists led by Jack Corliss and Robert Ballard, who were expecting to find warm water seeping from the seabed near the ridge crest. What they found instead was something far more dramatic and far more consequential for the history of science. The vents were surrounded by dense communities of organisms, giant tube worms, mussels, clams, and bacterial mats, thriving in total darkness at depths of more than 2,000 meters. The water emerging from these vents exceeded temperatures of 370 degrees Celsius, yet it did not boil because the extreme pressure at depth, roughly 250 atmospheres, kept it in a liquid state. When this superheated fluid met the near-freezing ambient water, the dissolved minerals precipitated out, forming towering chimneys of metal sulfides that could grow several meters tall. The most spectacular of these are the black smokers, vents that produce dark, mineral-laden plumes resembling columns of smoke rising from the seabed. The discovery of hydrothermal vents overturned one of the most fundamental assumptions in biology, that all life on Earth ultimately depends on sunlight and photosynthesis. Around these vents, dense communities of organisms thrive in total darkness, sustained not by photosynthesis but by chemosynthesis, the process by which bacteria derive energy from the chemical reactions between hydrogen sulfide and other compounds in the vent fluid. Giant tube worms, some exceeding 2 meters in length, cluster around the vent openings, their bodies existing symbiotic bacteria that convert the chemical energy of the vent fluid into organic matter. Blind white crabs and specialized shrimp swarm over the mineral deposits. Microbial mats coat the surrounding rock. These ecosystems exist entirely independently of the sun, powered instead by the heat and chemistry of the Earth's interior. They represent a fundamentally different model of life, one that could, in principle, exist on any planetary body with liquid water and geological activity, regardless of whether that body receives any sunlight at all. The acoustic environment around hydrothermal vents is complex and noisy. The eruption of superheated fluid through the vent opening creates a turbulent jet that generates broadband noise. The precipitation of minerals as the hot fluid meets cold water produces crackling and hissing sounds. The cracking and settling of newly formed chimney structures as they grow and collapse under their own weight creates impulsive sounds. The movement of organisms through the water, the clicking of crabs, the rasping of shrimp, adds biological noise to the mix. Some researchers have proposed that the cumulative acoustic output of a large vent-fed yield could contribute to the ambient sound budget of the deep ocean in ways that are not fully appreciated. Could a particularly large or unusually configured vent system produce a resonant tone that propagates through the SOFAR channel with enough power to be detected across the Pacific? The answer is theoretically possible, but the specific configuration required to produce the spectral characteristics of Upsweep has not been identified in any known vent field. The numbers are striking. The acoustic power required to achieve the observed detection range of Upsweep would be orders of magnitude greater than anything measured from known hydrothermal systems. A typical black smoker generates acoustic power in the range of fractions of a watt to a few watts. The Upsweep signal, detected across thousands of kilometers of ocean, even after accounting for the efficiency of the SOFAR channel, implies a source power that is far higher, possibly hundreds or thousands of watts of acoustic output. Either the source is far more powerful than any documented vent, or the propagation conditions in the southern Pacific are exceptionally favorable, channeling the sound with an efficiency that exceeds normal expectations, or the mechanism is not a simple hydrothermal vent at all, but something more energetic, more focused, and more unusual. The second avenue of investigation involves submarine volcanic eruptions. Unlike hydrothermal venting, which is a relatively continuous process, volcanic eruptions are episodic events that can release enormous amounts of energy in a short period. Submarine eruptions are surprisingly common. The mid-ocean ridge system produces new oceanic crust at a rate of several centimeters per year along its entire 65,000-kilometer length. Most of this volcanism goes unobserved because it occurs deep beneath the ocean surface, in complete darkness, far from human eyes and human instruments. Before the advent of hydrophone monitoring, these eruptions were invisible, detectable only after the fact through geological surveys that revealed new lava flows on the seabed. Submarine eruptions produce a wide range of acoustic signals. The explosive interaction between magma and seawater generates broadband sounds that can be detected at great distances. The slow effusion of lava onto the seabed produces lower frequency tremor as the molten rock flows and cools, cracking and hissing as it solidifies. The collapse of newly formed volcanic structures, pillow lavas and lava tubes and volcanic cones creates impulsive sounds as the cooling rock contracts and fractures, and the degassing of dissolved volatiles from the magma as carbon dioxide, sulfur dioxide, and water vapor bubble out of the molten rock and into the surrounding water produces a range of frequencies that depend on the rate of gas release, the depth of the source, and the size and behavior of the resulting bubbles. The degassing mechanism is particularly relevant to Upsweep because it can, under certain conditions, produce ascending tones. When a gas bubble is released from magma at great depth, it enters the water column at high pressure. As the bubble rises and the pressure around it decreases, it expands. The natural resonant frequency of a gas bubble in water depends on its size, with smaller bubbles oscillating at higher frequencies than larger ones. As the bubble expands during its ascent, its resonant frequency changes. If we consider a continuous stream of bubbles being released from a volcanic vent, each one rising and expanding, the collective acoustic output could include frequency components that change over time in a way that might resemble an ascending tone. The precise relationship between bubble size, depth, rising speed, and the resulting acoustic frequency is complex, governed by equations that involve the density of the gas, the density of the surrounding water, the surface tension at the gas-water interface, and the viscosity of the water. Models of volcanic degassing have been constructed to test whether this mechanism could produce the specific characteristics of upsweep. The results are mixed. The general concept works in broad outline. A continuous release of gas from a volcanic source could produce frequency-modulated acoustic signals, but the details do not match well. The rate at which the frequency ascends in the upsweep signal, the duration of each sweep, and the regularity of the pattern all present challenges for the degassing model. Natural bubble release from a volcanic source would be expected to produce variable, somewhat random signals, not the strikingly regular, repeating pattern that characterizes upsweep. Volcanic degassing is typically chaotic, with bubbles of varying sizes released at irregular intervals, producing a noisy broadband signal rather than the narrowband, pure-tone sweeps that upsweep exhibits. The model works in concept but fails in the specifics. A third possibility moves away from geology entirely and considers whether the upsweep sound could have a biological origin. The ocean is home to an enormous diversity of sound-producing organisms, many of which have been documented only recently. Blue whales, the largest animals on Earth, produce calls at frequencies as low as 14 Hz, well within the frequency range of the upsweep signal. Fin whales produce repetitive, low-frequency pulses that can be detected across entire ocean basins. Various species of fish produce sounds using swim bladders, specialized muscles, and other anatomical structures. Snapping shrimp collectively generate one of the loudest sustained sounds in the ocean. The deep ocean is far from silent, and the biological contribution to its acoustic environment is enormous. The biological hypothesis has been largely dismissed by the scientific community for several reasons, each of which is substantial. The spectral characteristics of upsweep do not match the known vocalization patterns of any identified marine species. Whale calls, while they can be low in frequency and powerful in amplitude, have characteristic patterns that reflect the biology of the animal producing them. A blue whale call has a specific structure, a specific duration, a specific frequency modulation pattern that is unique to the species and that varies in recognizable ways between populations and individuals. Upsweep does not match any of these patterns. Its frequency sweep is too regular, too narrowband, and too mechanically repetitive to be easily attributed to a living organism. Furthermore, biological sounds typically exhibit variation over time that reflects the behavioral state of the producing organism. An animal calling to attract a mate produces a different pattern than one calling to warn of danger or to maintain contact with a social group. These variations are fundamental to the biological function of the sound. Upsweep, by contrast, is strikingly uniform, repeating the same basic pattern with minimal variation, a characteristic more consistent with a physical or geological mechanism than a biological one. A living creature that produced the same sound without variation for more than 30 years would be biologically unprecedented. The amplitude of the upsweep signal also argues against a biological source. The signal has been detected by hydrophones separated by thousands of kilometers, implying either an extraordinarily loud source or extremely efficient propagation. While blue whale calls can be detected at great distances, the implied source level of upsweep would exceed the capabilities of any known marine organism by a significant margin. The loudest known biological sound producer in the ocean is the sperm whale, whose echolocation clicks can reach source levels of approximately 236 decibels, referenced to 1 micropascal at 1 meter. The implied source level of upsweep, while uncertain due to the distance between the source and the recording hydrophones, appears to be comparable to or greater than this, sustained continuously rather than produced in brief pulses. No known marine organism can sustain such output. But the dismissal of the biological hypothesis is not absolute. The deep ocean is home to species that have never been observed alive by human scientists. New species are discovered every year in deep-sea surveys, and the vast majority of the deep ocean has never been surveyed at all. The possibility that an unknown organism could produce a sound with the characteristics of upsweep is extremely unlikely based on current understanding, but current understanding is built on observations of less than 5% of the deep ocean floor. When 95% of an environment has never been directly observed, definitive statements about what it contains must be made with caution. The biological hypothesis remains on the table, however far back on the table it has been pushed. A fourth avenue of investigation examines the role of ocean-ice interaction. The Southern Ocean, where the upsweep source is believed to be located, is bordered by Antarctica, a continent surrounded by some of the most dynamic ice formations on Earth. Icebergs calving from the Antarctic ice shelves produce enormous acoustic signals as they crack, split, and grind against the seabed or against each other. These signals can propagate through the SOFAR channel over vast distances, arriving at distant hydrophones as complex modulated tones that can be difficult to classify without detailed analysis. The bloop, another famous unidentified ocean sound detected in 1997, was eventually attributed to the cracking of Antarctic ice, a large-scale icequake event, and this attribution was widely accepted after detailed comparison with other recorded icequake signals from known ice sources. Could upsweep be an ice-related phenomenon? The seasonal variation in the signal's amplitude initially seems to support this idea. Ice activity in the Southern Ocean peaks during the transition seasons, when temperature changes are driving the expansion and contraction of ice sheets, the calving of icebergs, and the breaking of sea ice. Spring brings the breakup of winter sea ice, while autumn brings the refreezing and the stresses that accompany it. This seasonal pattern of ice activity aligns, at least roughly, with the observed pattern of upsweep being strongest in spring and autumn. The coincidence is worth noting. However, the spectral characteristics of icequakes do not match those of upsweep. Icequakes typically produce broadband, impulsive signals, short bursts of energy spread across a wide range of frequencies, the acoustic equivalent of a crack or a boom. They are chaotic, irregular, and variable, reflecting the chaotic nature of ice fracture itself. Upsweep is narrowband and sustained, a continuous train of ascending tones with remarkable regularity and spectral purity. The waveform of upsweep is simply too regular, too uniform, and too spectrally pure to be easily explained by the mechanical fracturing of ice. Moreover, the estimated source location of upsweep is distant from the major ice shelves of Antarctica by thousands of kilometers, while icebergs can drift far from the continent, carried by the Antarctic circumpolar current and driven by winds. The consistency of the source location over decades suggests a stationary or nearly stationary origin. An iceberg drifting through the Southern Ocean would change position continuously, and the estimated source location would shift accordingly. The stability of the upsweep source coordinates over more than 30 years argues strongly against a drifting ice feature. If an iceberg were the source, the signal would have moved. It did not. A fifth and more speculative possibility involves resonance within the geological structure of the seabed itself. The ocean floor is not a uniform slab of rock. It is a complex, layered structure composed of sediment, basalt, gabbro, and deeper crustal material, permeated by cracks, fissures, lava tubes, and cavities formed by volcanic activity over vast periods of time. Along the mid-ocean ridges, the rock is particularly fractured and porous, riddled with passages through which seawater circulates, driven by the heat of the underlying magma. This circulation, known as hydrothermal circulation, extends for kilometers beneath the seabed and plays a critical role in regulating the chemistry of the ocean. It is conceivable that the interaction between seawater and these complex geological structures could produce sustained, resonant tones under the right conditions. Imagine a system in which seawater enters a cavity in the rock through a narrow opening, driven by the pressure difference between the interior of the cavity and the surrounding ocean. As the water flows through the opening, it vibrates, much as air vibrates when blown across the mouth of a bottle. The frequency of this vibration depends on the dimensions of the opening and the volume of the cavity, and if these dimensions change along the length of the passage, the system could produce a tone that sweeps upward in frequency as conditions shift. This is the geological resonator hypothesis, and it is appealing because it can potentially explain the spectral purity of the signal, the ascending frequency pattern, and the long-term persistence of the sound. A specific variant of this hypothesis proposes that the resonator is a lava tube, a hollow tunnel formed when the surface of a lava flow solidifies, while the molten interior drains away. Lava tubes can be enormous. On land, some lava tubes extend for tens of kilometers, with diameters of 10 meters or more. Submarine lava tubes, while less well studied, are known to exist along mid-ocean ridges, and some may be even larger than their terrestrial counterparts. A lava tube partially filled with water, with one or more openings to the ocean, could in principle act as a resonant cavity, producing tones that depend on its dimensions and the flow of water through it. But the geological resonator hypothesis, like all the others, is unverified. No specific cavity, lava tube, or geological structure has been identified at the estimated source location that matches the required dimensions. The hypothesis predicts that a specific physical structure exists at a specific location on the seabed, a structure with specific dimensions that produce the specific frequencies observed in the upsweep signal. This prediction could be tested through direct survey, using multi-beam sonar to map the seabed in detail, using remotely operated vehicles to inspect the seafloor visually, using instruments to measure the acoustic environment at close range. But no such survey has been conducted. The estimated source region remains one of the most remote, least surveyed patches of ocean floor on the planet. The catalogue of NOAA's unidentified ocean sounds provides additional context for the upsweep mystery, placing it within a broader pattern of acoustic anomalies that have emerged from the deep ocean during the modern era of hydrophone monitoring. Each of these sounds illuminates the broader challenge of acoustic identification in an environment as vast and opaque as the deep sea. The bloop, detected in 1997, was for years the most famous of these sounds. Its extremely powerful ultra-low frequency signal led to widespread speculation about possible biological origins, with popular media and internet forums seizing on the idea that an unknown deep-sea creature of enormous size could be responsible. The bloop was several times louder than the loudest known biological sound, which fueled the speculation. The scientific explanation, arrived at after years of careful analysis, attributed the bloop to a large ice quake, the cracking of a massive piece of Antarctic ice. The explanation was arrived at by comparing the spectral characteristics of the bloop with recordings of known ice quakes from the Antarctic region, and the match was convincing. Slow down, also detected in 1997, is a sound that decreases in frequency over a period of approximately 7 minutes, the reverse of upsweep's ascending pattern. Its estimated source location is in the remote southwestern Pacific, and the leading hypothesis attributes it to the scraping of a large iceberg against the ocean floor, a process known as ice grounding. As the iceberg moves and the angle of contact changes, the frequency of the resulting sound changes, producing the slow descending tone that gives the signal its name. Julia, detected the same year, produces a waveform that, when compressed in time and shifted to audible frequencies, sounds strikingly similar to a human moaning or calling out. This resemblance, combined with the mystery of its origin, made Julia a favourite of internet speculation. The leading hypothesis attributes it, like the bloop and slow down, to ice-related processes, though the specific mechanism remains uncertain. The train, a sound detected in 1997 that resembles the distant rumble of a locomotive, was detected in the same region as several of the other anomalous sounds, and is believed to originate from the interaction of ice with the seabed or with other ice features. The whistle, a brief ascending tone also detected that year, has characteristics that partially overlap with upsweep but is far less persistent, appearing in the data only briefly before vanishing. Upsweep stands apart from this group in two important respects. First, it predates the others by 6 years, having been present in the data from the very beginning of NOAA's hydrophone program in 1991. The other named sounds were not detected until 1997. Second, Upsweep has persisted for far longer than any of the others. The bloop appeared briefly and then fell silent. Slowdown and Julia have not been reported in recent recordings, but Upsweep has continued, diminished in amplitude, but still present, still repeating its ascending pattern more than 3 decades after it was first heard. This persistence is what makes Upsweep unique among the unidentified ocean sounds. It is not a transient event. It is an ongoing phenomenon, a feature of the deep Pacific acoustic environment that has outlasted most of the other anomalies by decades. Something is wrong with our assumptions about how well we know our own planet. The Upsweep sound is a reminder that the ocean remains a place where fundamental questions can go unanswered for decades, not because the questions are unimportant, not because the technology to answer them does not exist, but because the ocean is simply too vast, too deep, too remote, and too expensive to explore with the thoroughness that would be needed to solve every mystery it presents. But the Upsweep mystery does not exist in isolation. The deep ocean is filled with phenomena that challenge the boundaries of scientific understanding, features so strange that they would seem like fiction if they had not been directly observed. Each of these phenomena offers a lesson about the nature of deep-sea science, about the gap between what we expect to find and what actually exists in the abyss, and about why a sound that has been repeating for 30 years can remain unresolved. Consider the brine pools of the deep ocean floor. In several locations around the world, particularly in the Gulf of Mexico and the Mediterranean Sea, there are depressions on the seabed that are filled with water so dense with dissolved salt that it forms a distinct layer, a pool of brine sitting on the ocean floor beneath the normal seawater above. The boundary between the brine and the overlying water is so sharp that it looks, to a camera on a remotely operated vehicle, exactly like the surface of a lake, complete with a shoreline where the brine meets the surrounding sediment. The effect is surreal, a lake at the bottom of the sea, with its own surface, its own waves, and its own toxic chemistry. The salinity of these brine pools can be 4 to 5 times that of normal seawater. The dissolved salts, primarily sodium chloride and magnesium chloride, come from ancient salt deposits buried beneath the seabed, remnants of ancient seas that evaporated in the geological past. As seawater percolates through the sediment and contacts these deposits, it dissolves the salt and carries it to the surface of the seabed, where it accumulates in depressions to form the pools. The chemistry of the brine is hostile to most life. The concentrations of salt and other dissolved minerals are lethal to most organisms. Animals that inadvertently swim into a brine pool are often killed quickly by the osmotic shock, their bodies preserved by the brine in a state of eerie suspension, visible on the pool's surface. Yet life exists even here. Around the edges of some brine pools, dense communities of mussels and tube worms have been found, sustained by chemosynthetic bacteria that thrive on the chemicals dissolved in the brine. These organisms have adapted to conditions that would kill most life on Earth. They exist at the extreme boundary of what biology can tolerate, and their presence serves as a reminder that the deep ocean is capable of supporting life in environments that seem, by any reasonable standard, uninhabitable. The relevance of brine pools to the Upsweep mystery is not direct. There is no suggestion that brine pools are producing the sound, but the lesson they offer is important. The deep ocean contains features that were not predicted by theory, not imagined by scientists before they were discovered, and not explicable by the models that existed at the time of their discovery. Brine pools were discovered by accident, encountered during submersible dives that were focused on other objectives. Their existence was a surprise, and the ecosystems that surround them were a further surprise. The deep ocean has a long history of defying expectations, and the Upsweep sound is one more entry in that history. Consider also the creatures that inhabit the deepest parts of the ocean, organisms that defy the physical constraints that limit life on the surface. In the Hadal Zone, at depths exceeding 6,000 meters, life persists under pressures that would destroy most biological structures. The proteins in the cells of hadal organisms must fold and function under conditions that would denature the proteins of surface organisms. The cell membranes must maintain their integrity under pressures that would compress them into rigidity in any surface creature. The biochemical solutions that hadal organisms have developed to cope with these pressures are the subject of active research, and many remain poorly understood. Among the most striking inhabitants of the hadal zone are the giant amphipods, crustaceans that can reach lengths of more than 30 centimeters, far larger than their relatives in shallower waters. These animals are scavengers, feeding on the rare organic matter that reaches the trench floor. When a whale carcass or a fish sinks to hadal depths, the giant amphipods arrive in swarms, consuming the food source with an efficiency born of scarcity. Their gigantism, a phenomenon known as deep-sea gigantism, is not fully understood. Several hypotheses have been proposed, including the effects of cold temperatures on metabolic rate, the absence of predators that would select for smaller body size, and the advantages of larger body size in an environment where food is scarce and widely dispersed. None of these hypotheses has been conclusively proven. The supergiant amphipod, Alicella gigantea, is perhaps the most dramatic example. This creature, reaching lengths of up to 34 centimeters, was first described from specimens collected in deep-sea trenches and has been documented at depths exceeding 7,000 meters. Its existence was not predicted by biological models, and its size, in an environment of extreme pressure, cold, and food scarcity, challenges assumptions about the limits of biological adaptation. The deep ocean, it seems, does not read the textbooks. And then there are the snailfish. In recent years, researchers have captured video footage of snailfish living at depths exceeding 8,000 meters in the hadal zone. These small, translucent fish, their bodies soft and gelatinous, their bones partially dissolved by the extreme pressure, represent the deepest living fish ever documented. Their bodies have been described as looking almost ghostly, hovering in the darkness of the trench with a slow, deliberate movement that belies the crushing force of the water around them. The biochemistry that allows their proteins to function at such pressure involves the accumulation of trimethylamine N-oxide, a compound that stabilizes protein structure under extreme conditions. This adaptation was not understood until recently, and the full range of biochemical strategies employed by hadal organisms remains a subject of ongoing investigation. These biological discoveries are relevant to the Upsweep mystery because they demonstrate a consistent pattern in deep-sea science. Again and again, direct observation of the deep ocean reveals phenomena that were not anticipated by theory. The organisms found at hydrothermal vents were not predicted. The brine pools were not predicted. The extent and diversity of hadal zone life was not predicted. Each discovery expanded the boundaries of what scientists considered possible, and each required revisions to existing models and assumptions. The Upsweep sound exists in the same conceptual space, a phenomenon that does not fit neatly into existing categories, that resists explanation by existing models and that awaits the direct observation that might finally reveal its source. Consider, for one more example, the enigmatic structures off the coast of Yonaguni Island in Japan. In 1986, a diver named Kihachiro Aratake discovered a massive underwater formation approximately 25 meters below the surface off the southern coast of Yonaguni, the westernmost inhabited island of Japan. The formation consists of flat terraces, sharp edges, right angles, and what appear to be stairways carved into the rock, all of which give the impression of a man-made structure, a pyramid or a stepped monument submerged beneath the sea. The Yonaguni Monument, as it came to be known, has been the subject of intense debate since its discovery. Marine geologist Masaki Kimura of the University of the Ryukyus has argued that the formations are artificial, the remnant of a civilization that was submerged when sea levels rose at the end of the last ice age. Other geologists, notably Robert Schoch of Boston University, have argued that the formations are entirely natural, the result of the fractured sandstone splitting along its natural planes to create the illusion of architectural features. The debate over the Yonaguni Monument has continued for decades, with neither side producing evidence that has convinced the other. The formations are accessible, photographed extensively, and have been visited by numerous scientists and divers. And yet the fundamental question, natural or artificial, remains contested. If a debate about a structure that can be directly observed, touched, and measured can remain unresolved for decades, it should come as no surprise that a sound originating from the inaccessible depths of the remote southern Pacific remains unexplained. The Yonaguni case illustrates a broader truth about scientific investigation. Direct observation, while necessary, is not always sufficient to resolve a question. When the evidence is ambiguous, when multiple interpretations are consistent with the data, resolution requires either new evidence or new methods of analysis, and both take time. The deep ocean is the ultimate repository of ambiguous evidence. Its phenomena are observed indirectly, through instruments rather than eyes. Its features are mapped at low resolution, if they are mapped at all. Its processes operate at timescales that may exceed the duration of any individual scientific career, and its sheer vastness means that the probability of stumbling upon the right feature at the right time with the right instruments is small. The specific challenge of identifying an acoustic source in the deep ocean deserves examination because it illuminates why a sound that has been detected for more than 3 decades can remain unexplained even in an era of advanced technology. When a hydrophone records a signal, it captures not just the original sound, but also every distortion that the ocean has imposed on that sound during its journey from source to receiver. The ocean is not a uniform medium. It is layered with temperature gradients, salinity gradients, and pressure gradients that cause sound waves to bend, refract, and reflect as they travel. A signal that originates as a clean, simple tone at the source may arrive at the hydrophone as something more complex, its waveform altered by the passage through thousands of kilometers of structured water. Separating the characteristics of the source from the characteristics imposed by the propagation path is one of the fundamental challenges of ocean acoustics. And for a signal like Upsweep, where the source location is known only approximately and the propagation path crosses some of the least studied water in the world, this separation is exceptionally difficult. Multipath propagation adds another layer of complexity. A sound wave traveling through the SOFAR channel does not follow a single straight path from source to receiver. It follows a curved path, bending upward and downward as it passes through the sound speed minimum, and it may arrive at the receiver via multiple paths of different lengths. Each path produces a slightly different version of the original signal, arriving at slightly different times, and the recorded signal is the sum of all these arrivals. For a brief, impulsive sound, multipath propagation produces a series of distinct echoes that can be separated and analyzed individually. But for a continuous, repeating signal like Upsweep, the multiple arrivals overlap and interfere with each other, creating a composite waveform that is more difficult to decompose into its constituent parts. The spectral analysis of such a composite signal may reveal features that do not exist in the original source signal, artifacts of propagation rather than characteristics of the source. Distinguishing between these possibilities requires either a detailed model of the propagation path, which in turn requires detailed knowledge of the ocean structure along that path, or recordings from multiple hydrophones at known positions, which can be used to reconstruct the source signal through a process analogous to triangulation in reverse. Both approaches have been attempted for Upsweep, and both have produced results that are suggestive but not definitive. The ambient noise environment of the deep ocean further complicates the analysis. The ocean is never silent. Wind-driven waves generate a continuous background of noise at the surface. Distant shipping contributes a low-frequency hum that pervades entire ocean basins. Seismic activity on the ocean floor produces transient pulses that can mask or distort other signals. Marine organisms contribute their own sounds, from the low moans of whales to the collective crackling of shrimp beds. Against this backdrop, identifying and characterizing a specific signal requires sophisticated signal processing techniques that can separate the target signal from the background noise. For Upsweep, this separation is aided by the signal's distinctive spectral characteristics. Its narrow bandwidth and ascending frequency pattern make it relatively easy to identify in a spectrogram. But spectrograms reveal only the time-frequency structure of a signal. They do not reveal the mechanism that produced it, the distance it has traveled, or the distortions that the ocean has imposed on it during transit. A spectrogram is a description, not an explanation. Given these challenges, one might ask why no dedicated research expedition has been mounted to investigate the Upsweep source directly. The answer lies in the economics and logistics of deep-sea research. A research vessel capable of operating in the remote southern Pacific, equipped with the instruments needed to survey the seabed and characterize the acoustic environment at close range, costs tens of thousands of dollars per day to operate. A comprehensive survey of the estimated source region, covering enough area to identify the specific geological feature responsible for the sound, would require weeks or months of ship time, plus the cost of the instruments, the personnel, and the analysis of the resulting data. The total cost of such an expedition would easily exceed several $million, a substantial investment for a single scientific question, however fascinating. Funding agencies allocate their resources based on criteria that include scientific impact, practical relevance, and the likelihood of success. The Upsweep mystery, while intriguing, does not have obvious practical applications. It does not threaten human health or safety. It does not bear on climate change, fisheries management, or mineral resource extraction, the issues that drive much of the current investment in ocean science. And the likelihood of success of actually finding and identifying the source is uncertain. The source region is enormous, the seabed in that area is poorly mapped, and there is no guarantee that a survey would find anything definitive. These factors combine to make the Upsweep investigation a difficult sell in the competitive world of research funding. The sound persists, the questions remain, and the proposal sits unfunded in a filing cabinet somewhere, waiting for the day when scientific curiosity alone is considered sufficient justification for the expense. The history of science offers parallels that are both encouraging and sobering. The cause of continental drift, first proposed by Alfred Wegener in 1912, was not accepted by the scientific mainstream for more than 50 years. Wegener had the observations, the matching coastlines, the fossil distributions, the geological correspondences between continents separated by thousands of kilometers of ocean. What he lacked was a mechanism, a physically plausible explanation for how continents could move through the solid rock of the ocean floor. The mechanism, plate tectonics, driven by convection currents in the mantle and seafloor spreading at the mid-ocean ridges, was not established until the 1960s, when new technologies for mapping the ocean floor and measuring the magnetic properties of rocks provided the evidence that Wegener's observations had always demanded. For half a century, the right answer existed but could not be proven, because the technology and the will to gather the necessary evidence did not yet coincide. The Upsweep mystery may be in a similar position. The right hypothesis may already have been proposed. The geological resonator, the lava tube, the volcanic degassing mechanism. One of these may be essentially correct, but proving it requires evidence that can only be gathered through direct investigation of the source region, and that investigation has not been conducted. The parallel with continental drift is imperfect but instructive. In both cases, the key constraint is not the absence of ideas but the absence of data, and the absence of data is not a failure of intellect, but a consequence of the practical difficulties of studying the most remote and inaccessible parts of the planet. The pattern repeats throughout the history of ocean science. Before 1977, no scientist predicted the existence of thriving ecosystems around hydrothermal vents, because no one had ever looked. Before the deployment of deep-sea cameras in the mid-20th century, the abyssal plains were assumed to be lifeless deserts. Before the development of multi-beam sonar in the 1970s and 80s, the detailed topography of the ocean floor was essentially unknown, and entire mountain ranges and canyon systems lay hidden beneath kilometers of water, unsuspected and unmapped. In every case, the reality of the deep ocean turned out to be far more complex, far more dynamic, and far more surprising than theory had predicted. The common thread is that assumptions built on incomplete data were consistently wrong, and they were corrected only when new technology made direct observation possible. The upsweep sound sits squarely in this tradition, an anomaly that persists because the observations needed to explain it have not yet been made, a question that the ocean holds in reserve until someone arrives with the right instruments and the right funding and the patience to look. Each of the 5 avenues of investigation explored for upsweep, hydrothermal venting, submarine volcanism, biological sources, ocean ice interaction, and geological resonance offers a partial explanation. Each has strengths that make it plausible and weaknesses that prevent it from being accepted as definitive. The scientific process demands convergence, a point at which multiple lines of evidence point unambiguously to a single explanation. For upsweep, that convergence has not occurred. The evidence points in the general direction of volcanic or geological activity on the Pacific-Antarctic ridge, but it does not point to a specific mechanism, a specific feature, or a specific process with the certainty that science requires. The answers are there, somewhere beneath the surface, somewhere along the Pacific-Antarctic ridge, somewhere in the complex geology of the deep seabed. But reaching them requires resources, commitment, and time on a scale that the scientific community has not yet been able to muster. And so the sound continues, and the questions remain open, and the ocean keeps its secret with the quiet confidence of a place that has all the time in the world. There is a map of the world that most people carry in their minds, a map shaped by satellite photographs and nature documentaries, and the general confidence of a species that has walked on the moon and sent robots to Mars. In this mental map, the Earth is known. The continents have been explored, the mountains climbed, the rivers charted, the forests catalogued. The age of discovery is over. There is nothing left to find. This map is wrong. The ocean covers approximately 71% of the Earth's surface. It contains roughly 97% of the planet's water and provides the habitat for the vast majority of its living biomass. The average depth of the ocean is approximately 3,700 meters, deep enough to submerge most mountains and all but the tallest skyscrapers. At its deepest point, the Challenger Deep in the Mariana Trench, the ocean floor lies nearly 11,000 meters below the surface, a distance greater than the height of Mount Everest above sea level. If Everest were placed at the bottom of the Challenger Deep, its peak would still be submerged beneath more than 2,000 meters of water. The ocean is not merely deep. It is deep on a scale that defies the ordinary human experience of space and distance. Deep enough that the pressure at the bottom exceeds 1,000 atmospheres, deep enough that the temperature hovers just above freezing, deep enough that no sunlight has ever reached the floor. And yet, despite the ocean's dominance of the planetary surface, despite its importance to the climate, to the chemistry of the atmosphere, to the survival of virtually every ecosystem on Earth, the vast majority of the ocean floor has never been directly observed. The figure most commonly cited in the oceanographic literature is that less than 25% of the global seabed has been mapped at a resolution comparable to what is available for the surface of Mars. Some estimates place the figure even lower, suggesting that as little as 5 to 10% of the deep ocean has been surveyed with the multi-beam sonar systems that can reveal the fine-scale structure of the seafloor, the ridges and valleys, the volcanic cones and collapse craters, the sediment flows and fault scarps that define the landscape of the abyss. This disparity is not an accident. It is the direct consequence of the physics of exploration. Electromagnetic radiation, the medium that makes satellite mapping of land surfaces and other planets possible, does not penetrate seawater beyond a few tens of meters. Visible light is absorbed within the first 200 meters of the water column. Radar signals, the basis for satellite altimetry, reflect from the ocean surface but cannot penetrate it. To map the ocean floor, scientists must use sound, sending acoustic pulses from a ship-mounted transducer down through the water column and measuring the time it takes for the echo to return. This is the principle behind sonar, and it is the only technology currently available for mapping the deep seabed at high resolution. Satellite altimetry provides a crude alternative. The surface of the ocean is not perfectly flat. it is shaped by the gravitational pull of the features beneath it, with subtle bumps and depressions that mirror the topography of the seabed. A large seamount, with its greater mass, pulls the ocean surface upward slightly, creating a barely detectable rise in sea level above it. A trench, with its deficit of mass, creates a corresponding depression. By measuring the height of the ocean surface with extreme precision using radar altimeters on satellites, scientists can infer the general shape of the ocean floor. This technique has been used to produce global maps of the seabed that reveal the major features, the mid-ocean ridges, the deep trenches, the fracture zones, the large seamount chains. But the resolution of satellite altimetry is coarse, typically on the order of several kilometers, meaning that features smaller than this threshold are invisible. A volcanic cone 1 kilometer in diameter, a lava field covering a few square kilometers, a fissure in the rock that serves as a geological resonator, none of these would be visible in satellite-derived maps of the ocean floor. To detect these features, scientists must use ship-based multi-beam sonar, which can achieve resolutions on the order of tens of meters, depending on the depth and the configuration of the instrument. A modern multi-beam sonar system mounted on the hull of a research vessel can map a strip of seabed roughly twice as wide as the water is deep. In 4,000 meters of water, this means a swath approximately 8 kilometers wide. To map the entire ocean floor at this resolution, a research vessel would need to traverse every portion of the ocean in overlapping strips, a task that has been estimated to require roughly 350 ship years of continuous survey, a number so large that it puts the challenge in perspective. The global research fleet does not have the capacity to complete this task in any reasonable timeframe, and the cost would be measured in billions of dollars. The Seabed 2030 Initiative, a collaborative project launched in 2017 with the goal of mapping the entire ocean floor by 2030, represents the most ambitious effort to date to close this knowledge gap. The project aggregates data from multiple sources, including dedicated survey vessels, commercial shipping equipped with multi-beam systems, autonomous underwater vehicles, and military datasets that have been declassified for civilian use. As of recent assessments, the initiative has achieved coverage of approximately 25% of the global seabed, a significant improvement over the roughly 6% that had been mapped when the project began, but still far from complete coverage. The pace of mapping has accelerated in recent years, driven by advances in autonomous vehicle technology and the increasing willingness of commercial and military operators to share their data. But the remaining 75% of the ocean floor includes many of the most remote and least trafficked regions, including the southern Pacific, where the Upsweep source is believed to be located. The implications of this knowledge gap for the Upsweep mystery are profound. The estimated source location of Upsweep lies in one of the most remote patches of ocean on Earth, far from shipping lanes, far from the usual survey tracks of research vessels, and far from the coastal regions where most oceanographic research is concentrated. The seabed in this area has been mapped by satellite altimetry, revealing the general features of the Pacific-Antarctic ridge, but the high-resolution multi-beam data that would be needed to identify specific geological structures, a lava tube, a fissure, a resonant cavity, does not exist for most of this region. The answer to the Upsweep mystery may be sitting on the ocean floor, a physical structure with specific dimensions and specific acoustic properties, waiting to be found by a sonar beam that has not yet passed over it. The comparison with the surface of Mars is instructive, and for those who care about the health of our planet, troubling. The entire surface of Mars has been mapped at a resolution of approximately 100 meters per pixel by orbiting spacecraft, and selected regions have been mapped at resolutions as fine as 25 centimeters per pixel. Every crater, every canyon, every volcanic feature on Mars is known, catalogued, and available for study. The same cannot be said for the ocean floor of the Earth, despite the fact that the ocean floor plays a critical role in processes that directly affect human civilization, including the regulation of global climate, the cycling of carbon and nutrients, the distribution of marine life, and the frequency and intensity of earthquakes and tsunamis. We know the topography of a dead, airless planet 225 million kilometers away, better than we know the floor of the ocean that covers most of our own world. Let that sink in. This is not merely an academic complaint. The practical consequences of the mapping gap are real and ongoing. Submarine volcanic eruptions occur without warning because the volcanoes that produce them have never been surveyed. Seamounts that pose hazards to submarine navigation remain uncharted. Hydrothermal vent fields that support unique biological communities. Communities that may contain organisms of pharmaceutical or biotechnological interest exist undiscovered on the seabed. Geological features that influence the circulation of deep water and thereby the transport of heat and nutrients through the global ocean remain unmapped and unaccounted for in climate models. And sounds that emanate from the deep ocean, sounds that have persisted for decades, remain unexplained because the geological features that produce them have never been identified. The funding disparity between space exploration and ocean exploration makes the mapping gap even more striking. Global spending on space programs runs into the hundreds of billions of dollars annually, encompassing national agencies, private companies, and international collaborations. The resources dedicated to ocean exploration are a fraction of this figure. The entire annual budget of NOAA, the agency responsible for monitoring the health and behavior of the world's oceans and atmosphere, is smaller than the annual budget of most national space agencies. The research fleet that maps the ocean floor, studies its ecosystems, and monitors its acoustic environment operates under constraints that would be considered unacceptable in any other domain of science that addresses questions of comparable importance. The ocean is not ignored because it is unimportant. It is underexplored because the technology required to study it is expensive. The logistics are punishing, and the political will to fund deep ocean science at the level it deserves has never materialized. The Upsweep sound is, in a sense, a product of this funding gap. The mystery persists, not because it is unsolvable, but because solving it would require an investment that the scientific enterprise has not been prepared to make. The situation is compounded by the distribution of acoustic monitoring infrastructure. The hydrophone arrays that NOAA operates in the Pacific are concentrated in a relatively small number of locations, optimized for the detection of signals in the equatorial and northern Pacific. Coverage in the southern hemisphere is sparse. The Indian Ocean has even fewer permanent acoustic monitoring stations. The Atlantic Ocean is somewhat better served owing to the legacy of the SOSUS network, but large areas remain unmonitored. The Arctic Ocean, where retreating sea ice is opening new waters to both acoustic propagation and human activity, has only recently begun to attract sustained monitoring attention. If the Upsweep signal is representative of the kinds of persistent acoustic phenomena that the ocean produces, then the handful of anomalous sounds catalogued by NOAA since 1991 may represent only a small sample of a much larger population of unidentified signals, sounds that occur in unmonitored regions, at unmonitored frequencies, or at amplitudes below the detection threshold of existing instruments. The exploration of the deep ocean in the modern era has been carried out primarily by a small number of research institutions operating a limited fleet of specialized vessels and vehicles. The submersible Alvin, operated by the Woods Hole Oceanographic Institution, has been in service since 1964 and has made more than 5,000 dives, but each dive covers only a tiny area of seabed, typically a few hundred meters in any direction. Remotely operated vehicles, tethered to surface ships by cables that carry power and communication signals, can reach greater depths and stay submerged for longer periods, but they too are limited in the area they can cover. Autonomous underwater vehicles, which operate independently of surface ships and can survey larger areas, represent the most promising technology for expanding the pace of ocean floor mapping, but their deployment has been limited by cost, reliability, and the logistical challenges of operating in the open ocean. The Challenger Deep, the deepest point in the ocean, has been visited by only a handful of expeditions in all of human history. The first descent was made by Jacques Piccard and Don Walsh in the Bathyscaphe Trieste in January of 1960, reaching a depth of approximately 10,916 meters. The second crewed visit did not occur until more than 50 years later, when filmmaker and explorer James Cameron made a solo descent in the Deep-Sea Challenger in 2012. Subsequent visits have been made by Victor Vescovo and others, but the total number of humans who have visited the deepest point in the ocean remains in the single digits. By comparison, more than 600 people have traveled to outer space, and 12 have walked on the surface of the moon. The bottom of the ocean, a place on our own planet, a place that influences the climate we live in and the food we eat, is less visited than the surface of another world. Let that sink in. Consider what this means for the study of deep ocean acoustics. Every sound that has ever been generated beneath the surface of the ocean has propagated through a medium that is, for the most part, unobserved. The creatures that produce biological sounds in the deep ocean are largely unpataloged. The geological features that produce abiotic sounds are largely unmapped. The physical processes that generate ambient noise, the slow creaking of the crust, the interaction of water with rock, the movement of sediment down submarine slopes, are understood in general terms but documented in detail at only a handful of locations. The acoustic environment of the deep ocean is, in the most literal sense, unknown territory. Scientists study it the way astronomers once studied distant galaxies, by collecting what signals reach their instruments and constructing models to explain what those signals might mean. The models are informed by theory and by the few direct observations that have been made at accessible sites, but they are models nonetheless, simplified representations of a reality that is vastly more complex than any model can capture. The upsweep sound is a single thread in this vast, unmapped acoustic tapestry. Its detection was a consequence of having instruments in the right place at the right time, listening at the right frequencies. The NOAA array that first recorded upsweep in 1991 was designed to monitor a specific region of the Pacific for a specific range of frequencies, chosen to capture the kinds of signals that were expected to be scientifically interesting, primarily seismic events and large-scale oceanic processes. Upsweep was not expected. It appeared in the data as an anomaly, an uninvited guest in a recording session that was focused on other matters. This accidental nature of the discovery raises an uncomfortable question. If one of the most persistent and distinctive acoustic phenomena in the recorded history of the ocean was discovered by accident, in the first year of a monitoring program that covered a tiny fraction of the ocean, how many other phenomena exist that have never been recorded because the instruments were not present to capture them? The honest answer is that no one knows. The dishonest answer, the answer that the mental map encourages, is that we would already know about them if they existed. The technological barriers to comprehensive ocean monitoring are formidable, but not insurmountable. Advances in acoustic sensor technology have produced hydrophones that are smaller, cheaper, and more durable than the instruments used in the original NOAA deployments. Fiber optic cables laid on the ocean floor for telecommunications can be adapted to serve as distributed acoustic sensors, converting the entire length of the cable into a continuous listening device. Autonomous underwater vehicles equipped with acoustic sensors can be programmed to patrol specific regions, recording the acoustic environment over periods of weeks or months. The technology exists, in principle, to monitor the acoustic environment of the entire deep ocean. What does not exist is the institutional framework, the funding, or the political will to deploy these technologies at the scale required. The ocean remains under-monitored, not because monitoring is impossible, but because it has not been prioritized. The instruments sit in laboratories and warehouses, ready to be deployed but lacking the funding and the institutional support to put them in the water. The expertise exists. The technology exists. The scientific questions, including the origin of the upsweep sound, are well-defined and tractable. What is missing is the commitment to treat the deep ocean as what it is, the largest and least understood environment on Earth, a place where fundamental discoveries remain to be made, and where the answers to persistent mysteries lie waiting beneath kilometers of dark, cold water, patient and undisturbed. The deep ocean is also a place where time operates differently than it does on the surface. Geological processes on the ocean floor unfold over timescales that dwarf human experience. The mid-ocean ridge system, which produces new oceanic crust as tectonic plates diverge, operates at a rate of a few centimeters per year, roughly the speed at which fingernails grow. A lava flow that erupts on the seabed today may not be covered by sediment for thousands of years. A cavity in the rock that acts as an acoustic resonator may have been formed by volcanic activity that occurred before the emergence of modern humans. The processes that drive the upsweep sound, whatever they are, may have been operating for far longer than the 30-plus years during which the sound has been recorded. The signal may have been present in the ocean for centuries or millennia before the invention of hydrophones made it detectable. The upsweep is not necessarily a recent phenomenon. It may be ancient, a feature of the deep Pacific acoustic environment that predates not only its detection, but the entire technological civilization that eventually noticed it. This temporal perspective reframes the mystery. The question is not only what produces the upsweep sound, but how long it has been producing it. If the source is a geological resonator, a lava tube or cavity that vibrates as seawater flows through it, then the sound may persist for as long as the structure remains intact, which could be tens of thousands or even hundreds of thousands of years. The gradual decline in amplitude that has been observed since 1991 could reflect a slow change in the structure, erosion of the cavity walls, accumulation of sediment in the openings, or a gradual shift in the flow of water through the system. Or the decline could reflect changes in the propagation path rather than changes at the source, shifts in ocean temperature or salinity that alter the efficiency of the SOFAR channel along the path between the source and the recording hydrophones. Without direct observation of the source, these possibilities cannot be distinguished. The decline in amplitude also carries a more unsettling implication. If the upsweep sound is indeed weakening over time, it is possible that the source is in the process of shutting down. The structure that produces the sound may be deteriorating, its openings closing, its resonant properties changing as the geology shifts beneath it. If this is the case, then the opportunity to identify the source may be finite. The sound that has been repeating for more than 3 decades may not repeat forever. It may fall silent before anyone arrives to discover what produced it, and the mystery will become permanent, an unanswered question preserved in the archives of NOAA alongside the acoustic recordings that documented it. The ocean is patient, but it is also indifferent. It does not wait for us to be ready. There is also the question of what else the ocean is producing that we have not yet heard. The NOAA hydrophone array, as sensitive as it is, covers only a small fraction of the ocean's volume. The sensors are concentrated in the equatorial and northern Pacific, with far less coverage in the southern hemisphere. The Atlantic and Indian Oceans are even less well monitored. The Arctic Ocean, increasingly accessible as sea ice retreats, remains acoustically uncharted in many areas. If one persistent, unexplained sound was detected in the first year of hydrophone monitoring, the 1991 deployment that captured Upsweep from its very first day of operation, how many other sounds might be present in the ocean that have never been recorded because no hydrophone has been deployed in the right place to hear them? The Upsweep signal was detected because the sensors happened to be sensitive to its frequency and happened to be positioned within the detection range of its source. Change either of those parameters, shift the frequency, or move the source, and the sound would have gone unnoticed, another whisper in the darkness of the deep ocean, heard by no one. The implications extend beyond acoustics into every domain of deep ocean science. Marine biologists estimate that millions of species in the ocean remain undescribed, from microorganisms to invertebrates to fish that inhabit the deep midwater and the abyssal plains. New species are documented every year, not only in the least explored regions, but occasionally even in waters that have been studied for decades. The discovery of an entirely new phylum of marine organisms, not merely a new species or genus, but a new phylum, in the late 20th century demonstrated that the taxonomic framework for ocean life was far from complete. Geological surveys of the mid-ocean ridges have revealed volcanic features and tectonic structures that were not predicted by existing models. the discovery of asphalt volcanoes on the floor of the Gulf of Mexico in 2003, structures that erupt not lava but natural asphalt and petroleum, was entirely unexpected and required new categories of geological classification. The deep ocean is a place where the unexpected is routine, where the discovery of phenomena that overturn existing models is not the exception but the norm. This pattern has a direct bearing on the Upsweep mystery. Every hypothesis that has been proposed for the origin of the Upsweep sound is based on known mechanisms: hydrothermal venting, volcanic degassing, ice mechanics, biological acoustics, geological resonance. Each of these mechanisms is well understood in its general operation, but incompletely characterized in the specific conditions that prevail at the Upsweep source location. It is entirely possible, perhaps even likely, that the actual source of the Upsweep sound involves a mechanism or a combination of mechanisms that has not been considered, a process that is unique to the specific geological and oceanographic conditions at that particular point on the Pacific-Antarctic ridge, a process that will seem obvious in retrospect, but that cannot be predicted from first principles because the relevant conditions have never been observed. The history of deep ocean science is replete with such cases. Phenomena that were not predicted until they were discovered. Discoveries that required new categories of understanding. Explanations that seemed impossible until they were shown to be real. The Upsweep sound may require not just new data but a new idea, a hypothesis that no one has yet conceived because the observations that would inspire it have not yet been made. The philosophical weight of this knowledge gap is considerable. Humanity defines itself in part by its capacity to understand the world, to observe, to measure, to explain. The scientific revolution, the intellectual transformation that began in the 16th and 17th centuries, and that continues to this day, was founded on the principle that the natural world is comprehensible, that its phenomena can be observed, its patterns identified, its causes determined. This principle has been spectacularly vindicated in domains ranging from astronomy to genetics, from particle physics to evolutionary biology. But the deep ocean challenges this principle in a fundamental way. Not because the ocean is inherently incomprehensible, it is not. The same physical laws that govern the surface world govern the deep sea. The challenge is that comprehension requires observation, and observation requires access, and access to the deep ocean is so difficult, so expensive, and so limited that entire categories of phenomena exist beyond the reach of routine scientific inquiry. The Upsweep sound is comprehensible in principle. It obeys the laws of physics. It has a source, a mechanism, a physical explanation waiting to be found. But finding it requires going to a place that humans have not yet gone, with instruments that have not yet been deployed, to observe a process that has not yet been witnessed. The gap between what is knowable and what is known, between what can be understood and what has been understood, is the gap that the Upsweep mystery occupies. It is a gap that says more about the limits of human infrastructure than about the limits of human intelligence. The deep ocean is not merely unexplored. It is unexplored in a way that most people do not appreciate, a way that makes it fundamentally different from the unexplored regions of the land surface. When we speak of unexplored land, we mean land that has not been visited by scientists or mapped in detail, but which can in principle be observed from the air or from space. Even the most remote rainforest or the most inaccessible mountain peak can be seen in satellite imagery, but the ocean floor cannot be seen from above. It can only be mapped from below, by instruments that must be deployed in the water at enormous cost and with enormous logistical effort. The ocean floor is, in a meaningful sense, invisible, hidden beneath kilometers of water that block every form of electromagnetic radiation that humans use to observe the world. To know what is on the ocean floor, we must go there, physically, or with instruments that we lower into the water, and we have gone to so few places that our knowledge of the seabed is riddled with gaps large enough to contain entire mountain ranges, entire ecosystems, entire geological processes that we have not yet imagined. The Upsweep sound is a product of one of those gaps. It emerges from a region of the ocean floor that has not been surveyed in detail, a region that lies beyond the reach of routine observation, in a part of the world where research vessels rarely travel, and scientific attention is rarely directed. The sound is a message from the unknown, a signal from a part of the planet that we have not yet managed to examine. Its persistence, more than 3 decades and counting, is a testament to the durability of whatever process produces it, and its refusal to be explained by any existing hypothesis is a testament to the limits of knowledge built on indirect observation alone. We hear the sound, we record it, we analyze its spectral characteristics with the finest instruments available, and still we do not know what it is. The upsweep sound occupies the space between hearing and understanding, a space that is far wider than most people realize, a space that the ocean has always controlled and shows no sign of relinquishing. The age of discovery is not over. It has barely begun in the place where it matters most, the vast, dark, silent expanse that covers most of the world and holds most of its secrets. There is a quiet assumption that runs through modern civilization, an assumption so deeply embedded that most people never think to question it. The assumption is that the Earth is known, that the planet on which we live, the planet on which every human civilization has risen and fallen, the planet whose resources sustain every living thing, has been thoroughly explored, comprehensively mapped, and fundamentally understood. This assumption informs the way we teach geography, the way we fund science, the way we think about the relationship between humanity and the natural world. And this assumption is wrong. The upsweep sound is one small piece of evidence against this assumption, but it is a powerful one. Here is a sound that has been recorded continuously for more than 3 decades. A sound that is detectable across thousands of kilometers of ocean. A sound with distinctive characteristics that set it apart from every other identified acoustic phenomenon in the sea. And no one knows what it is. The leading hypotheses, geological activity, volcanic processes, resonant structures on the seabed remain unverified. The source region has never been surveyed with instruments capable of identifying the mechanism. The mystery persists, not in some distant corner of the universe, not on some unexplored moon of Jupiter, but here, on our own planet, in our own ocean, within reach of our own technology, if only we chose to deploy it. This is not science fiction. This is the documented reality of deep ocean science in the 21st century. The implications of the upsweep mystery extend far beyond the question of what produces a particular sound in a particular patch of ocean. They reach into the foundations of how we understand our relationship with the planet. For most of human history, the ocean was a barrier, a boundary, a source of food and danger and mystery. The age of exploration, beginning in the 15th century, treated the ocean primarily as a surface to be crossed, a medium of transportation between the landmasses where human activity was concentrated. The depths below were of interest only to mythmakers, and, later to a small community of naturalists who dredged the seafloor from ships and speculated about what lived in the darkness below. The systematic scientific study of the deep ocean is barely a century old. The first sustained effort to understand the ocean floor as a geological and biological system, rather than simply as a surface to be charted, began with the British Challenger expedition of 1872 to 1876. And even that groundbreaking voyage could only sample the ocean at discrete points, lowering instruments over the side and hauling up whatever they captured. In the century and a half since the Challenger expedition, the tools available for studying the deep ocean have advanced enormously, from simple dredges and sounding lines to multi-beam sonar, remotely operated vehicles, autonomous underwater vehicles, satellite altimetry, and deep-sea submersibles capable of reaching the very bottom of the ocean. And yet the fundamental challenge remains the same. The ocean is too large, too deep, and too opaque for any existing technology to survey comprehensively. Every measurement is a point in a vast unsampled space. Every observation is a keyhole view into a room that stretches for thousands of kilometers in every direction. The advances in technology have been real and substantial, but they have not closed the gap between what is known and what remains to be discovered. They have, in some ways, widened it, because each new tool reveals new categories of phenomena that previous tools could not detect, and each new category of phenomena raises new questions that require further investigation. The more we learn about the deep ocean, the more we realize how much there is to learn. The Upsweep sound embodies this paradox. The hydrophone technology that detected it was, at the time of its deployment, among the most sensitive acoustic instruments ever placed in the ocean. The signal processing techniques used to analyze it were sophisticated and well tested. The scientists who studied it were experts in their field, trained in the interpretation of acoustic data from the deep sea. And yet the sound resists explanation. Not because the scientists are inadequate, not because the instruments are insufficient, but because the information needed to solve the puzzle, the detailed geological survey of the source region, the close-range acoustic measurements, the direct observation of the mechanism in action, has not been gathered. The mystery is not a failure of science. It is a failure of access. The funding disparity between the exploration of outer space and the exploration of the deep ocean is a reflection of priorities that are, at the very least, debatable. Both domains are vast. Both are hostile to human presence. Both contain mysteries that challenge the boundaries of knowledge. But space exploration captures the public imagination in a way that ocean exploration does not. The images returned by planetary probes, the drama of rocket launches, the romance of walking on another world, these have a cultural power that the study of the deep seabed cannot match. A photograph of the surface of Mars receives more attention than a sonar map of the mid-ocean ridge. A robot on the surface of Mars receives more public funding than a remotely operated vehicle on the floor of the Pacific. This is not a criticism of space exploration, which has produced extraordinary scientific discoveries and has expanded the human understanding of the cosmos in ways that are genuinely profound. It is an observation about the allocation of resources and the consequences of that allocation for the study of the planet we actually inhabit. If even a fraction of the resources devoted to space exploration were redirected to the deep ocean, the Upsweep mystery could likely be solved within years, not decades. A dedicated expedition to the source region, equipped with modern multi-beam sonar, a deep-rated remotely operated vehicle, and an array of acoustic instruments, could survey the relevant section of the Pacific-Antarctic ridge, identify geological structures of interest, and measure the acoustic environment at close range. The data collected would almost certainly narrow the field of hypotheses to one or two candidates, and might well provide the definitive answer. The technology exists, the scientific framework exists, the will and the funding do not. The irony is sharp. The same civilization that tracks the orbits of asteroids millions of kilometers from Earth with exquisite precision cannot explain a sound that has been repeating in its own ocean for more than 3 decades. The same species that has mapped the craters of Mercury and the ice plumes of Enceladus has not mapped the seabed where Upsweep originates. The same scientific enterprise that can detect gravitational waves from the collision of black holes billions of light years away cannot identify the geological feature responsible for a narrow-band, acoustic signal emanating from a known region of the Pacific. These contrasts are not meant to diminish the achievements of physics or astronomy, which are extraordinary by any measure. They are meant to illuminate the extraordinary neglect of the deep ocean, a neglect that is all the more striking because the ocean is not remote. It is here. It is beneath the ships that carry our goods, beside the cities where we live, above the floor that may hold answers to questions we have been asking for decades. The Upsweep sound does not require a journey of millions of kilometers. It requires a journey of a few thousand meters straight down, into waters that are dark and cold and pressurized, but that are, by the standards of interplanetary travel, practically next door. The Upsweep mystery also carries a philosophical lesson about the nature of scientific knowledge and the relationship between evidence and explanation. Science does not progress in a straight line from question to answer. It progresses in fits and starts, driven by the availability of data, the development of new instruments, and the occasional flash of insight that connects observations in a way that no one had previously considered. The history of science is filled with mysteries that persisted for decades or centuries before being resolved, not because the resolution was conceptually difficult, but because the necessary observations had not yet been made. The nature of lightning was debated for thousands of years before Benjamin Franklin's experiments in the 18th century. The cause of disease was mysterious, until the development of the microscope revealed the existence of microorganisms. The mechanism of heredity was unknown until the discovery of the structure of DNA in the 20th century. In each case, the answer was there all along, embedded in the natural world, waiting for the right instrument or the right observation to make it visible. There is a tendency, particularly in popular culture, to treat unsolved scientific mysteries as evidence of the supernatural, as signs that the natural world contains forces that are fundamentally beyond the reach of human understanding. This tendency is understandable. Humans are storytelling creatures, and a mystery without an explanation invites narratives that fill the void with wonder, with dread, with the tantalizing possibility that the world is stranger and more magical than science allows. The Upsweep sound has attracted its share of such narratives, stories about ancient civilizations on the ocean floor, about vast creatures lurking in the abyss, about alien machinery operating beneath the waves. These stories are imaginative, and they reflect a genuine human need to make sense of the unknown, but they are not necessary. The natural world, examined closely and honestly, is stranger and more wonderful than any supernatural narrative could be. The reality of the deep ocean, with its brine pools and its giant amphipods and its lightless ecosystems powered by the heat of the earth itself, is more extraordinary than any fictional tale of monsters or lost cities. The Upsweep sound does not need a supernatural explanation to be remarkable. The fact that a sound has been emanating from the floor of the Pacific Ocean for more than 30 years, detected by instruments designed for entirely different purposes, analyzed by some of the most capable scientists in the field, and still not explained, is remarkable enough. It is a reminder that the natural world retains the capacity to surprise, to challenge, and to humble the species that presumes to understand it. The Upsweep sound is also a mirror. What we see in the mystery reflects what we value, what we prioritize, and what we choose to ignore. A civilization that can put rovers on Mars but cannot survey the floor of its own ocean has made choices about where to direct its attention and its resources. These choices are not inherently wrong. The exploration of space has yielded discoveries that have expanded the horizon of human knowledge in ways that few other endeavors can match. But the choices have consequences, and one of those consequences is that mysteries like Upsweep persist, year after year, decade after decade, while the technology to solve them sits idle for want of funding and attention. The Upsweep sound is waiting for its Franklin, its microscope, its moment of revelation. The answer is there, somewhere on the floor of the southern Pacific, encoded in the geology of the seabed and the physics of sound propagation through water. It is not hidden in the sense of being deliberately concealed. It is hidden in the sense that the part of the planet where it exists has not yet been examined with sufficient care. The ocean does not keep secrets out of malice. It keeps them out of indifference. The indifference of a physical system that operates according to its own rules, at its own pace, without regard for the curiosity of the species that lives on its surface. The sound continues. The source remains. The explanation waits. And the ocean, as it has for all the billions of years of its existence, does not care whether we find it or not. Somewhere in the southern Pacific Ocean, in a stretch of water so remote that the nearest inhabited land lies thousands of kilometers away, something is making a sound. It has been making this sound since at least 1991, when the first hydrophones capable of detecting it were lowered into the deep water. It may have been making this sound for centuries before that, or for millennia, or for longer still. No one knows. No one has been there to check. The sound rises. That is the defining characteristic, the signature that gives it its name. Each individual tone sweeps upward in frequency over a period of several seconds. A narrowband whisper ascending through the deep water, cycling and repeating with a regularity that has no parallel among the known sounds of the ocean. The pattern does not falter. It does not stop. It does not vary in the way that biological sounds vary, driven by the hunger or fear or desire of a living thing. It repeats with the mechanical patience of a process that has no awareness of itself, no intention, no audience. The ocean floor produces the sound, or something on it does, or something within it, and the sound travels upward and outward through the SOFAR channel, carried by the physics of temperature and pressure and salinity across thousands of kilometers of dark water to the instruments that wait and listen and record. In the decades since the sound was first captured, its amplitude has slowly declined. The ascending tones are still there, still repeating, still audible in the spectrograms that NOAA scientists produce from the raw acoustic data, but they are quieter than they were. The signal that was once strong enough to be detected clearly across the entire width of the equatorial Pacific is now fainter, diminished, as though the source is running down, like a clockwork mechanism losing its spring, or as though the channel through which the sound travels is changing in ways that attenuate the signal before it reaches the receivers. The decline is gradual, measured in fractions of a decibel per year, but it is real, and it raises the possibility that the sound will one day fall below the threshold of detection and vanish from the record entirely, leaving behind only the archived recordings and the unanswered questions that surround them. The thought that the sound might disappear before it is explained carries a particular weight. There is something unsettling about the idea of a mystery that resolves itself not through understanding but through silence, not through the triumph of investigation but through the quiet cessation of the phenomenon that prompted the investigation in the first place. If the upsweep sound falls silent, the question of its origin will not be answered. It will simply become unanswerable, a permanent entry in the catalogue of things that the ocean once produced and that humanity once noticed and that no one ever managed to explain. The archived recordings will remain, digital files stored on servers and backup drives, available for analysis by future scientists who may bring new tools and new perspectives to the puzzle. But the source itself will be silent, and without the active signal to guide them, future investigators will face an even more difficult task than the one that confronts researchers today. This is the urgency that the Upsweep mystery carries, an urgency that is not dramatic, not cinematic, not the kind that drives headlines or inspires emergency funding. It is the quiet urgency of a window that may be closing, slowly and without fanfare, in a part of the world that attracts almost no attention. The window has been open for more than 30 years. It may remain open for decades more, or it may close tomorrow. The geology of the deep seabed operates on its own schedule, indifferent to human timelines, and the process that drives the upsweep sound, whatever it is, will continue or cease according to the physics of rock and water and heat, not according to the readiness of human scientists to observe it. What the upsweep sound teaches, if we are willing to learn from it, is something about the relationship between hearing and understanding. We heard the sound in 1991. We have been hearing it every day since. We have recorded it, analysed it, graphed its spectral characteristics, estimated the coordinates of its source, debated its possible origins in scientific papers and conference presentations, and late-night discussions in the offices of Ocean Research Laboratory around the world. And still, after all of this, we do not understand it. We hear it, but we do not know what it is. The gap between hearing and understanding is wider than most people assume, and in the deep ocean, where observation is constrained by physics and access is constrained by economics, that gap can persist for a human lifetime or longer. The upsweep sound is not the most important scientific mystery of our time. It will not cure disease, avert catastrophe, or revolutionize technology. Its resolution, when it comes, will likely be a quiet affair, a paper published in a specialized journal, read by a few hundred acousticians and geologists, noted in the records of NOAA, and largely unnoticed by the wider world. The source will probably turn out to be something geological, a resonant cavity or a volcanic process that matches one of the existing hypotheses, and the explanation will be satisfying in the way that all good scientific explanations are satisfying, illuminating a connection between cause and effect that was always there, but that required the right observations to make visible. But the significance of the upsweep mystery lies not in the eventual explanation, but in what the mystery itself reveals about the state of human knowledge. It reveals that there are processes operating on our own planet, in our own ocean, that we cannot explain. It reveals that the technology to investigate these processes exists, but has not been deployed. It reveals that the gap between hearing and understanding, between detecting a phenomenon and comprehending its cause, can persist for decades, even in an era of extraordinary scientific capability. And it reveals that the ocean, the largest feature of the Earth's surface, the environment that regulates the climate, nurtures the majority of living species, and shapes the chemistry of the atmosphere, remains, in fundamental ways, unknown. The ocean has always been the keeper of human humility. It was the edge of the known world for ancient civilizations that mapped the stars and built great monuments but could not fathom what lay beyond the horizon. It was the graveyard of ships and sailors who ventured into waters they did not understand, trusting to skill and courage in an environment that rewarded neither. It was the last great barrier of the age of exploration, the domain that resisted mapping long after the continents had been charted and the poles had been reached. And now, in the age of satellites and supercomputers and artificial intelligence, the ocean remains what it has always been, a place where certainty dissolves and assumptions fail, and the limits of knowledge are drawn not by the boundaries of human intellect, but by the boundaries of human reach. The upsweep sound is a voice from that place. Not the voice of a creature, almost certainly, and not the voice of anything that intends to be heard. It is the voice of geology, of physics, of processes that operate in darkness and pressure and cold, beyond the sight of any living observer. It is the voice of a planet that is still, after all these centuries of study, capable of producing sounds that its most curious inhabitants cannot identify. It is the voice of the unknown, speaking in a language that we have recorded but not yet translated, a language written in frequency and amplitude and spectral purity, a language that the ocean speaks to itself in the permanent night of the deep Pacific. Somewhere beneath the surface of the southern Pacific, the upsweep sound continues. It rises through the water column, each tone ascending through the frequency spectrum with the same deliberate, unhurried pattern it has followed, since before anyone was listening. The water carries it outward through the SOFAR channel, dispersing it across thousands of kilometers of ocean, delivering it to the hydrophones that record it, and the scientists who study it, and the world that, for the most part, has never heard of it. The sound does not know that it is a mystery. The source does not know that it is sought. The ocean does not know, and would not care if it did, that a species on its surface has been listening for more than 3 decades, and still cannot say what it hears. The sound rises. The ocean listens to itself, and somewhere in the permanent darkness of the deep Pacific, far from sunlight and far from human eyes, the answer waits, patient and unhurried, as it has always waited.